Ladies and gentlemen, we're about to begin the second day of the Future of the Semiconductors Forum. Please have your seats.
Good morning, distinguished guests, esteemed speakers, and colleagues. Welcome to the second day of the Future of Semiconductors Forum here in Riyadh. It's truly inspiring to see such an impressive gathering of industry leaders, researchers, and innovators here. On the agenda for today, we have an exciting lineup of sessions that will explore some of the most cutting-edge development in the world of semiconductors. Before we begin, I would like to express my sincere gratitude to all of you for taking the time to be here with us today. Your presence and participation are invaluable. And now, without any further ado, let's dive into the first session of the day, and please join me in welcoming our esteemed speakers and moderators for the Future of Semiconductors starts here. First, we'll explore the realm of photonics in the session entitled Photonics from the Lighting to Quantum Technologies, moderated by Dr. Abdullah Al-Tamimi.
Good morning, everyone. Welcome to the second day of Future of Semiconductor Forum. So our first session, our keynote speaker for the first session, Professor Steve Denvers. I would like to invite him to the stage.
Thank you for inviting me to beautiful Riyadh and CAX. It's great to be here. So I'm very fortunate to be part of the Center of Excellence in 3-nitride photonics and electronics, and I'll talk today about some of the recent advances in 3-nitrides for both micro-LED and laser devices for display to quantum computing. This work, like I said, was supported by the CAX UCSB Center of Excellence in 3-nitrides, which includes a lot of professors, both from UCSB and CAX that are listed here, Professor Nakamura, Mishra, Speck, and at CAX, our colleagues Mughbel, Harbi, Al-Hassan, and Dr. Tabak running the clean room, of course. And then a long group of students and researchers at both institutes are supporting the results I'll show here today. So our center is focused on making the 3-nitrides into a smart and safe and sustainable future. And the applications that we're looking at span from RF and laser devices to LEDs. You heard yesterday from Professor Mishra about the power devices and the RF. Today I'll focus on the new applications for nitride LEDs, particularly micro LEDs for AR and VR, and also for AI communications as well. It's a new emerging area there. And in the lasers, I'll talk about how we've generated DFB lasers for quantum computing sources and atomic sources. Let's see, the laser pointers here is not working. So in the overview, we'll talk first. I'm going to start with the DFB laser, which stands for distributed feedback laser, and talk about how we've made a very manufacturable version of these lasers, which have very good line width characteristics that we believe can replace larger tabletop versions. The micro LEDs, I'll show you the progress we've made all the way down to now 1 micron in size, and then show you some of the recent high modulation bandwidth results, and that they're being looked at not just for displays, for communication links. And then we'll talk about some more of the future work. So let's start with the laser applications. So nitride lasers span a wide range all the way from 360 nanometers all the way into the green at 540 nanometers. Combined with the red lasers and the phosphides, one of the area for AR and VR is to make projection displays. So that's kind of where we started, but we were approached by several groups to develop the blue laser, make a narrower line width for what's called photonic integrated circuits that can be used for atomic sensing and atomic clocks in particular, things like Rydberg RF sensors and whatnot. We worked with Bunoy at KAUST on undersea communication with the lasers as well. So there's just a wide variety of applications for the laser that both in the kingdom but also abroad that really demand the need for a very narrow line width blue laser. And currently there is no blue DFB laser on the market. So the ultimate goal of this is to make quantum sensors. And one quantum sensor at UCSB is shown here. It's an atomic clock, and it's very big. It takes a whole bench top here, as shown on the right, and requires a couple $1,000 laser here, solid state laser, but nevertheless its frequency tripled to get to these wavelengths. And we'd like to replace this very expensive system, which at the end costs about $1 million. We'd like to replace that with a chip scale atomic clock that will cost on the order of about $10, so that everybody could have an atomic clock in their car someday or in your home someday. Why would you need it? Well, there's lots of quantum sensing applications coming that use both the Rydberg RF field sensing, but also strontium for atomic clocks. And you'll notice they all have the need for a 461 nanometer blue laser in the first stage to do a lot of these sensing applications. So why 3 nitrides? This view graph here on the right shows the wavelengths or energies that we can span with the nitride material system, as opposed to the traditional 3,5s of gallium arsenide. You could see indium nitride combined with gallium nitride and aluminum nitride span not only the entire visible spectrum, but a good portion of the ultraviolet portion as well. So if we can make lasers at these ranges, we can have a wide variety of new sources here. And so one thing you'll notice is that there's a large lattice change in the aluminum nitride to indium nitride, so that it makes the material very difficult to grow, but we're able to do that with some tricks that we'll show. And really developing shorter wavelengths has been one of the key programs of our center to basically move from the blue and into the ultraviolet eventually. So one of the ways we do that is we cut the crystal at different orientations. So in the upper right here, we see the traditional orientation. Here is the 001 orientation. We've selected for the blue and the green, we've selected these, what's called semi-polar orientation. So in the box here, on the upper right, it shows the 202 bar 1 orientation. And what that Miller-Bravais indices notes is that we cut the crystal then on this oblique plane, and we get very different quantum physics that arise. We change from the traditional C-plane lattice, which is shown here, and we go to the 202 bar, which is a more normal quantum well. And that's what our aim is, to make this structure here on the right, which shows a quantum well, which is much more like a square potential well. What that buys you is the ability to make much better laser devices, because the electron and hole then occupy the same space in real space. So this is the blue laser that we've grown by MOCVD. They now have MOCVD technology here at KAUST as well as KAUST. And this technology is a real key for the 3 nitride and the 3,5 technology in general. It's become the real workhorse in the industry to make these devices. And using that, we can grow this very complicated layer structure, which I want to point out. The real active region is where the action really is. It's these 2 quantum wells here in green that are 3.5 nanometers. These 2 quantum wells have an overlap of about 2.5% with the mode. So this red circle here shows the mode intensity. This is where the laser beam is going to come out of. It's just these 2 quantum wells. And we clad it with P and N type material on both sides. And this particular design has been evolving over the last 20 years to get high efficiency lasers. Now the part of this project that's very different is most lasers use what's called a Fabry-Perot mode cavity. This is a typical laser where you just make mirrors on the end and you have your gain medium. The distributed feedback laser shown on the right actually uses a grating etched into the laser structure where the reflection is not from the mirrors, but is from the grating itself, which is a multiple of a quarter wavelength of light, to give you the feedback. Now, this has the advantage that you'll see is that we'll be able to get much cleaner spectrum. So the Fabry-Perot mode here usually produces a laser with many modes, which is not good for quantum sensing. And so replacing that with this distributed feedback cavity, like I said again, where we make a very narrow pitch grading here, we can get a nice laser spectrum shown in the bottom right here with a single wavelength, single emission peak, and very narrow line width. So DFB lasers have been in development for about 20 years, so I'm showing you some of the efforts here in research. But they haven't been commercialized because lasers which have a grating buried in the structure, this was the first one done at Xerox, actually have very poor performance, and they didn't get to what's called continuous wave performance. And so you need a laser that's going to be continuous wave. And so at UCSB, we've been developing the grating not within the laser itself, but on the very top of the structure. We put a grating in the ITO, or in particular, we've now come with the one on the right. So this is one of my PhD students developed this HSQ technology, which then converts to silicon dioxide grating. And so the laser doesn't have any mirror on it, but instead has this grating. And so this embedded surface grating has given us the best results to date and let us get really good lasers. So it takes about a month to fabricate one of these devices. It's a little bit more complicated than a typical laser. And the real key to this technology was developing atomically smooth ITO on top here with a roughness of 300 picometers. And then embedding in that ITO, we embed basically a silicon dioxide. And the way you do that is you spin on a HSQ photoresist grating, use electron beam photolithography to pattern that grating, and then put ITO on top of that. And then you have your embedded grating here. And this is all done on top of the laser, so after processing. So this is the results then of our DFB laser. This is a continuous wave DFB laser, so you can see that at 150 milliamps, it breaks in from spontaneous, and you start getting stimulated emission here. And in particular, you get nice single mode, single frequency behavior up till about 200 milliamps, at which point you start to get multi-mode. But in this range, then, we have good lasers now that are good enough for quantum sensing application. In addition, the power output is very high. The earlier systems I showed you were like 10 milliwatts. This diode laser is able to put out 100 milliwatts of good single mode emission. And so this is a good source to use. And so the next big thing was, now that we have CW DFB lasers, are they narrowest? And so this shows the basically the frequency, the line width measurement. And you can see here that as you increase the power, there's an inverse relationship with power and the line width. We can now get down below a megahertz, and we're at 684 kilohertz. Here is the Lorentzian line width. So this is actually the lowest reported line width for a blue DFB laser. If we were a company, we would commercialize this, but since we're a university, we're working with other corporate partners to try to get this transferred to industry. But this will then lead to I believe, the evolution of single frequency DFB sources for multiple applications. And so what's the big deal? Why would you want to commercialize something like that? I know Saudis are real interested in commercializing it. Well, basically, you can replace these fairly big but expensive laser systems that are about $1,000. You could replace those with laser diodes that are about $10. So that really opens up mass markets if you can make these nice single frequency devices. So we still have some work to do in making these, for instance, tunable. So now we're working on making that tunable. But you can do things like collision sensing with these. You can do sensing of atom states. And even Google's looking at putting these in quantum computers. Okay, so that was the first half of my talk. And the last half, let me just talk about the other application, which I know is a topic several people here in the kingdom work on as well, which is micro-LEDs. What's a micro-LED? This one shows you what the applications are. It's basically making very, very small LEDs. So you all have these beautiful LED screens here. We'd like to shrink this LED screen we're looking at by 10,000-fold and basically make it so that you can put it on a matchstick. And so a couple companies have done that recently at Society for Information Display. They've made a projection display here, which is as big as a matchstick, and full color nonetheless. So you can then put these tiny displays into glasses and do projection on glasses. The other big application was Samsung released about 4 years ago. They released a TV. While I don't think it's the best application, nevertheless had beautiful application. This wall we're looking at right here, it's not a micro LED screen wall, but it's getting close. It's got about a millimeter pitch. This one here, it's about a 40 micron size LED pitch, so very high resolution. So these are the kind of coming applications from this technology as well. Key thing here is, again, what materials should be used. So those first micro LED screens I showed you actually used what's called aluminum gallium indium phosphide for the red, which is shown here in the right. And that actually is going to lead to one of the biggest problems with micro LED displays is if you use a different material system, you have to transfer 12 million chips to make that TV. And you have to do it in a different material system. And so these are called mass transfer. So it's very hard to place 12 million LEDs on a TV. If you can do it instead with one material system, and you don't have to change material system, you can do things like the projection display. Rather than 12 million chips, you can get away with one chip. So that's a huge advantage if we can switch all three colors. And so we've been working on making the red brighter because that was the big problem. Red was not efficient. In particular, it was about 1% when we started this project. Now we're out here in the red. We're at about 9% here at 600 and about 5% here at 620. And so there's now a potential to do the entire display on one chip. So micro LEDs have been touted as the next generation display, and it's been taking longer. A lot of people ask me, why is it taking so long? And I just tell them again, it's because you've got to place 12 million LEDs. It's too difficult to do. So we need to think of new ways. So a lot of people were thinking there was going to be an iWatch that was going to come out with displays, but the OLED has dominated there. And the reason is, I got an iWatch right here. OLED is good enough at 1,000 nits is the brightness here. So micro LEDs really should be only used where you need really high brightness because it's 100 times brighter than the OLED. And they offer much better efficiency. So things like displays for mobile phones or projection displays for glasses, I think is where it's going to end up because the OLED has been getting better. And 1,000 nits is where your TV is. So you don't need real high brightness. So you need to be smart about where you use these things. The other kind of developing story about micro LEDs is they weren't as efficient as the LED lights that you have in your rooms, which are about 50%. So it took us quite a few years, but in the blue in particular, you can see we're at about, we're actually at 50% now, but you can see a few years ago we were at 30%. We used some technology of what's called tunnel junctions that the moderator who introduced me, Dr. Al-Hassan, helped develop. And if you use tunnel junctions and combine it with atomic layer deposition, we can get really efficient LEDs now. And the micro LED looks like this. So it's all grown on one substrate. We put ALD here on the edge. We put silicon dioxide by ALD on the edge to passivate it. And then we actually put tunnel junctions on and we replace the ITO. And why do I say that was tunnel junction technology was important? It's because we can now get to 50%, 55% wall plug efficiency, which is almost 3 times that of OLED efficiency. So we can make not only extremely bright displays that are 100 times brighter than OLED, but they're 3 times more efficient. And that's the real promise. And so this shows you, in particular, over traditional ITO technology, which is what we use for LED lighting, which is in black. At the low current densities here, the tunnel junction technology really vastly outperforms the traditional ITO technology. And so it's basically going to be, gives you the ability to replace the transparent oxide in the semiconductor device. Last thing I'm going to talk about is scaling these down to even smaller. So I'd say the iPhone display needed 10 microns. We've scaled them all the way down to 1 micron. And so here's an array we've made. And so recently, rather than use this blue array here for display, because we fit so many in a small little area here, actually this is the width of a human hair is 65 microns. So you could see we can basically get in here about 42 by 42 array in something as big as a human hair and couple that with a fiber. So what we could do is get very good efficiencies now as we go from 10 to 1 micron, particularly in the red it actually gets, we get an increase from the light extraction. It goes from about 6% up to 10%. Green stays about flat. We think some strain relaxation is going on here in the red to give us better efficiencies. And this will be reported on or published this year. But in particular, we will look at using these for communication. And so what we've done is take that very small array I've showed you, and we've modulated it as we get smaller in size. And this shows you the advantage of going to smaller LED sizes. As you go from 100 microns here on the right to basically, this one's 5 microns, at high current densities, we can get a modulation speed of 280 megahertz. Well, that doesn't sound that impressive when you're comparing to a laser, which is like 10 gigahertz, but I just showed you how many, it's easy to make a 100 by 100 micro LED array. And so what we want to do is, and there's a company in the Bay Area started to try to commercialize this, is to make a massively parallel micro LED array. And you saw that in the width of a human hair, we can fit this very small array. That will give you a 2.8 terahertz link at very low cost. This will be a very low cost compared to laser diodes. And so we're talking to several of the AI companies and communication companies about how do you do a fiber bundle to drop down and couple. So a lot of it is going to be looking at this for now, not just displays, but for data communication. So with that, I'll summarize the work then I showed you is moving on into things beyond just the LED light bulb for your home. I think blue lasers will be very important for quantum computing and atomic sensing, and the micro LEDs will be used not just for display, but I think they'll be developed for high bandwidth Li-Fi as well. Thank you.
Thank you, Professor Steve. So would like to invite the second speaker for the session, Professor Yating Guan, please.
Thanks for the introduction. Where is the slides? All right, thanks for coming. So today I will talk about integrated photonics with on-chip lasers. This is a collaboration with UC Santa Barbara and Intel. So the rapid expansion of artificial intelligence and high-performance computing has created a huge demand for process capability and energy efficiency. So ChatGPT is a very prime example. So one search on ChatGPT generally consumes more than 10 times of energy consumption compared to a typical Google search, and with daily operation cost up to $700,000. So the global consumer internet traffic is growing rapidly, around 4-fold in the last 5 years, and already reached 4.8 gigabit per year in 2022. So if you imagine every gigabit of this data is a brick, and 4.8 trillion of the bricks will be able to create more than 1,000 gigawatts in China. So here's the challenge we have. So data center consumes a lot of power, around 2% of the overall electricity worldwide, and around 15 to 30% of the power spent on the interconnect. And the capabilities of electronic hardware, according to Moore's laws, doubles around 18 months. And the machine learning doubles around 3.4 months. So you see there's a huge gap between these two slopes, and these two very huge slope gap as actually the bottleneck for electronics that limits the future applications, including artificial intelligence and all the related applications. So integrated photonics provide a very promising alternative by leveraging its very high bandwidth up to 100 gigahertz and low power consumption down to sub-picojoule per bit and much better speed to efficiency compared to the state-of-the-art electronics. So integrated photonics is a very good platform because it's fully compatibility with CMOS processing and huge reduction in size, weight, power, and cost. So if you just now we are changing from this fragile and small 3-5 photonic circuits that you can just hold it into hand and to this 12-inch silicon wafers that provides you much better thermal and mechanical properties. But the problem is that, so you see the silicon is an interbank material, so naturally it's a very inefficient light emitter. So the best group 4 laser has a special current density around 300 kiloamp per centimeter square, which is around 3,000 times higher than the typical direct bank and 3-5 lasers. So to integrate 3-5 lasers with silicon photonics, there are various methods. So there are various methods, including hybrid integration, heterogeneous integration, and monolithic integration. Each has its own advantages and limitations from the alignment precision, the bonding requirement, and material compatibilities. So today, I will focus on our method of using quantum dot instead of quantum wells at the active region. So what is quantum dot? So quantum dot, okay, we don't have the animation here, but quantum dot is a zero-dimensional structure that can create this delta function density of states. So it's just like how we transition from the bulk materials to quantum wells, and now we are in a revolution to change from quantum wells to quantum dot that can create you much, much better performance, including high temperature operation up to 220 degrees C and very, very low stretch current density. But the most exciting point is that so the quantum dot has very, very small line width enhancement factor, which we call alpha factor. So for quantum well, it's around 3 to 5, but quantum dot is 15 times smaller. So this alpha factor is closely related to the critical feedback level that the 15 create 50 dB in the critical feedback level, so that when 90% of the light reflected back to the quantum dot laser. So you see, the laser is still working fine. But for quantum well lasers, even with minus 25 dB of the light reflected to the laser cavity, you see there's complete coherence collapse. So this is very important because the lasers now are not afraid of the reflection, so we don't need isolators in the photonic circuits that are bulky, expensive, and very difficult to integrate. So another very beautiful thing of quantum dot is the reduced lateral diffusion. So the quantum weld, the lateral diffusion length is around 10 micron, but quantum dot is 10 times smaller. So in case, well, in nanofabrication and materials, there's always defects. So when there is defects, the carriers move around in the plane in the quantum well can encounter this dislocation trap and get trapped here and no light emitted. But for quantum dot, so each quantum dot has very, very small diffusion length, so your chance to interact with the dislocation trap state is very slow. So like each dot just be here and they can emit efficiently. So here's a better example. So you see there's a very defective material. You see there's red points here and there all around. But even with this very high defect density, the quantum dot density is at least 2 orders of magnitude higher, so that the majority of the dots just stay here and don't interact with the defects, and they can emit efficiently. So because it's this property, so the quantum dot laser is quite stable. Our latest result with Intel show that we can achieve robust laser operation at 80 degrees C with more than 1 million hours of extrapolar lifetime, which is much higher than any integrated lasers on silicon. So there are a lot of progress for the single quantum dot devices on silicon, from optic pump structures to electronic pump structures, from the single devices to system demonstrations without isolators. And the quantum dot turned out to be not only very good material for lasers, but also good material for amplifiers and photodetectors. That is good for forming the fully integrated photonic circuits. And this is our current work with Intel to integrate the quantum dot lasers directly into the photonic circuits that are created by Intel, including the silicon modulators, germanium photodetectors, and all their silicon waveguides. So basically, we start with wafers from Intel and open areas for the bonding of quantum dot materials. And it's very important that we passivate the silicon photonics part, including the modulators, detectors, and at the same time, create very, very high performance lasers. So you see, like, we do a lot of optimization on the etching and the passivation so that we can have these nice tapers to couple the light from the quantum dot and the light was effortlessly coupled to the silicon photonics part and interact with the rest of the photonic circuits. So this is our first batch of laser device, laser performance, including this low threshold current of 4 milliamp, this good substrate ratio, and CW temperature. So this is just like our first round. But what I want to emphasize is it shows very promising for bandwidth of line width as well. So the one disadvantage of quantum dot is that generally the module bandwidth is limited. So even on the native substrate, it's only around 10 gigahertz. But you see, our first demonstration, even with very long cavities, without HR coating, without a BCP passivation, but we still got the record high bandwidth of 30 gigahertz, and that leaves out a lot of room to further improve this limitation of quantum dot. And the second is that, well, the alpha factor turned out to all be also closely related to line width. So you see, like, generally, the quantum well lasers, if you don't apply more strategies, the general line width is around megahertz. But we already got 26 kilohertz for our current devices, and our latest result in Nature Photonics paper has reduced this line width to just several hertz. So it's very important for a lot of narrow line width applications. So this just to summarize our result with the previous one. So just to ignore all the data, what I really want to emphasize here is that lasers with a silicon waveguide can perform much, much better for lasers without a silicon waveguide. So which means that there is synergistic relationship between the quantum dot devices and the silicon photonics that provides not only economic scale, but also performance requirement. To put it into even simpler words, so when you integrate the lasers on the silicon photonics, you not only get a bigger, cheaper, and a better substrate, you also get better lasers. So it's a win-win. So we continue this work with Intel when I come back from UC Santa Barbara to KAUST. So over the 2 years, we still collaborate with them. So we use their 300 millimeter silicon photonics platform, get 12-inch wafers and core into 4-inch wafers so that we can process in the universities. So we believe that by changing from the bonding quantum well lasers to quantum dot on silicon structure, there will be a lot of opportunities to build upon what has already achieved with quantum well lasers to improve performance and reduce cost. So currently, the biggest driver in photonics is still the datacom. But the dense device integration with on-chip lasers will also be very important for a number of future applications, from optical computing, biochemical sensing, quantum computation, optical-based LiDAR, etc., for the efficiency, stability, and scalability. So just to conclude, so we do a lot of progress on the integrating of lasers with silicon photonics. So laser integration will be critical for a number of applications. And we are advancing the technologies of replacing quantum dot with quantum wells, just like how quantum well lasers replace the bulk materials. And we are committed to combine the quantum scale while maintaining the highest yield for the future semiconductors and photon integrated circuits. Thank you so much for your attention.
Ladies and gentlemen, please welcome our next speaker, Dr. Salim Ghaffar Rao.
Superconducting quantum circuits fabrication and reduction in the quantum coherent losses. I'm from Department of Physics, King Fahd University. Outline of my today's talk is superconducting quantum circuits, TLS losses, major obstacle in developing a superconductor-based quantum computers. Then I will talk about how you can reduce these TLS losses and you can improve the coherence time of the superconducting quantum circuits. Growth and regrowth of the oxides. Oxides are the major host of the TLS losses. And then finally, I will conclude it. So, outline of my today's, I think it's repeated. Yes, what is a qubit? So before I move on to the superconducting qubits, qubit is just simply a two-level system. And that can exist in a superposition state. Two-level system can be, I can be on the stage, I can be on the ground floor. But it's a two-level system. But two-level system which can exist in a superposition state. One of the natural two-level system is an atom. Electron can be in the first shell, can be in the second shell at the same time. This is the very basics of the chemistry. So this is a very natural and very useful qubit. Spin state of the electron is also a very useful qubit. Electron can have the spin up, spin down, and it can have both the states at the same time. NV centers, in a diamond, if you create these two defects, nitrogen and vacancy, so the atomic structure of this pair of N and V is like an artificial, like a natural atom. Ion trap is also another very interesting qubit. In addition to that, you can have the light as a two-state system. So there are many options available for the qubit. So these qubits have many advantages. For example, NV center has a very high coherence time, and you can operate them at room temperature. Ion trap, also very promising. But with all these qubits, the problem is how to fabricate a quantum computer. How to integrate it, onto the table or onto a chip. So there is a big issues in these platforms. Another, one of the most promising platform is a superconducting qubit. The superconducting qubit is nothing, it's just simply an LC circuit. So you just simply have an inductor and a capacitor, so it is a superconducting qubit. Only thing is, you have to operate this LC circuit in a quantum regime. So whenever you operate LC circuit in a quantum regime, it energy states are quantized. So this simple LC circuit is not a good qubit because energy spacing is equal. So you cannot control the energy states. For example, the system is in a ground state. If you give the photons, so if you give 2 photons, it will go from 0 to 2, 3 photons, 0 to 4, and so and so on. So you don't have the good control. So we need a non-linear oscillator. So that problem you can solve very easily if you replace the inductor by a non-linear inductor, which is typically a Josephson junction. So now, LC circuit with the Josephson junction is a non-linear LC oscillator, and which is a very useful qubit. And this qubit itself is on a small chip of millimeter by millimeter. You can see this bend, big chandelier structure, but this is not a quantum computer. Quantum computing chip is, again, few millimeter by few millimeter. So this is simply the idea. You have a quantum chip. You can see there's a big cylinder over there. So this cylinder is not a, you need it, this big structure, cylindrical big structure, just to cool it down, to just simply isolate it from the noise and so and so. Actually, quantum chip is a very small part over there. Okay, this is the quantum chip. The good thing about it is you can fabricate this quantum chip using conventional microfabrication technology. So you don't need anything new to fabricate the superconductor-based quantum chip. So in a superconducting quantum computing, when you're going to fabricate it with conventional microfabrication process, so one of the most important part of the fabrication is the Josephson junction. Josephson junction is nothing, it's just simply metal, insulator, metal junctions, but of a very specific dimensions. So this insulating layer, okay, which is somewhere here in the orange color, this insulating layer is of phi atomic layer. So the size is 200 micron by 200 nanometer by 200 nanometer, which is quite big, those who are working in a fabrication technology. But the critical is the thickness of the oxides, edge roughnesses, and so, because all those things are going to compromise on the coherence time of the qubit. So you can have one Josephson junction, you can have two Josephson junction in the qubit, it can be 3, it can be more, depending upon what type of qubit you are fabricating. With Josephson junction, you can fabricate many different types of qubits, but nowadays, the most promising qubit is the transmon qubit. So all Google, IBM, and all other, those who are working in the field of superconducting quantum computing, they are using the transmon qubit because it is very less sensitivity, okay, to the charge noise is almost negligible. Okay? So if you go to the last 2 decades, people tried different types of qubits, but the transmon is one of the most promising one because of very low charge noise. And then you can see somewhere here, okay, when you have a quantum chip, you have the LC circuit. So this one is the nonlinear LC circuit, other is the linear LC circuit. So superconducting quantum chips are nothing, they are just the LC circuits. So this is the structure of the superconducting one unit where you have the resonator and you have the qubit. So what you have on the superconducting quantum chip from the fabrication point of view, you have the coplanar waveguide resonators, which is very common structure for electrical engineers. They are using it for hundreds of different applications currently. So these resonators in the quantum computing, we use it as a readout, at a control, and for the entanglement of the qubit as well. You have the qubit. So coplanar waveguide resonator is just simply an LC circuit. Then you have the qubit, an active component, which you use to process the information. So it is nothing. It is just a nonlinear LC oscillators. Now, in a quantum computing, on this particular chip, we use microwave, but we operate these devices, okay, in a single microwave photon. So on a chip, we have only one photon, which is moving from one place to another place on the chip. So this one photon means, okay, the signal is very, very weak. So we need, okay, a quantum amplifier as well. So if this signal you are going to amplify with your conventional microwave amplifiers, okay, there is a lot of noise over there, and you will lose all the informations. So on the quantum chip, you have the quantum amplifier as well. But what is quantum amplifier? It is almost a linear oscillator. So on the quantum chip, okay, from the fabrication point of view, okay, we have all LC oscillators, and we have to operate them just in a quantum regime. So the transmon qubit, as I mentioned, so this is the micrograph SEM image of the transmon qubit. You can see this is the full structure, and the qubit, Josephson junction is a very small part. So basically in the transmon qubit, you have the Josephson junction. Josephson junction has the capacitance as well as inductance effect. So Josephson junction itself is an LC oscillators. But this LC oscillator is very sensitive to noise. So to overcome the noise, okay, we put a very big capacitor with it, just like as a wings of the plane. It's a very big structure. So this, if you put the big capacitors, okay, with this Josephson junction, we can overcome the problem of the charge noise, which was the big issue, okay, almost a decade ago. So this is something on my quantum chip. So you have the resonator, and you have the qubit, okay, and the qubit has two parts, Josephson junction and the superconductor. So you can see the fabrication is very straightforward and very simple. So different designs, okay, has been tested, okay, for this quantum chip. So you have the resonators, you have the control lines, you have the qubit. Everything is just an LC oscillator, nothing else. The physics of the QED is also very simple, okay? So this is, cavity QED is a very hot area of research in optics and particularly for physicists. It was the dream of the physicists. They want to study the single atom, okay, the quantum nature of the single atom. So the cavity QED is, okay, a very interesting subject for experimentalists as well as for theorists. So we can transfer all that knowledge without any modification to our circuit QEDs. So physics of the circuit QED is same as the cavity QEDs. Here you have the cavity, there we have the resonators. The physics of both of them is exactly the same. Here you have the artificial atom, there we have the, sorry, in case of a cavity you have the natural atoms, over there you have the artificial atom. So the good thing in a superconducting quantum circuit is it's all LC oscillators, and the physics is the physics of the cavity QEDs. Okay, you can transfer it without any modification. That's why you will not get any literature, okay, theory literature related to circuit QEDs, because all the knowledge of the cavity QEDs, you can transfer it as it is, okay, to the circuit QEDs. Now the question is, on this particular superconducting quantum chip, you have the resonator, dimensions are in micrometer. You have the Josephson junction, which you use to make a qubit or transmon qubit. Dimension is 200 nanometer by 200 nanometer. So these dimensions, okay, are nothing, okay, those who are working in the microfab technology. So the question is, why it is difficult to fabricate a quantum chip with millions of qubits? It shouldn't be an issue, because those who are working in the microfab technology, they can create billions of, okay, structures, they can repeat it. That's not a big deal. So, but why you cannot do it in a quantum computing? The reason is, if you have the more qubit on the quantum chip, okay, you lost the coherence, okay? So you need a high coherence time, okay? As of today, as you increase the number of the qubits on the quantum chip, you compromise on the coherence time. And that's a big compromise. You cannot process the information if the coherence time is very low. Second thing is, you need to entangle the qubit. In addition to superposition of the qubit, you need to entangle the qubits as well, okay? Because this quantum computer is exploiting, okay, two physical properties of a qubit, okay, superposition and the entanglement. When you have the more qubit, you compromise and these two things. Why you lost the coherence? The reason is low coherence time of the qubit is because the qubit is going to due to its controlled and uncontrolled interaction with the environment. So the qubit interact with its environment, and the qubit, you have to send the signal, okay, because you want to process the information. Okay, so whenever you're sending the information from the outside, so there is some noise in it. Okay, and because of that, okay, you compromise on the coherence time. Although there is a 4 to 5 order of magnitude improvement in the coherence time in last 2 decades, but still, okay, we are 1 or 2 steps away, okay, from the required coherence time. So you can see somewhere here, fabrication of the superconducting quantum chip is not an issue. Issue is the coherence time. If you can have the high coherence time, then superconducting quantum computer, you can fabricate it, okay, within no time, because semiconducting fabrication technology platforms, okay, can fabricate any kind of structures within no time. So I basically work on how to improve the coherence time. So coherence time is basically, we believe in this thing, and that is, of course, this is a theory, and one of the most promising theory is why the coherence time is less, because the qubit is going to interact, okay, with two-level systems in its vicinity, okay? So at low temperature and at single photon power, as I said, on my quantum chip, okay, when I'm processing the information, the signal is very weak. Signal is of 1 photon. So, and if that photon is going to couple, okay, with a defect in my material, so my informations are lost, okay? So I cannot do any kind of processing over there. So we use these resonators, okay, to measure how many TLS losses are there. So first we measure it, how many TLS losses are there, and then we try to mitigate it. We try to remove it. So what I do, I just simply make a design, okay, of some specimen already tested experimentally. Then we measure the quality factor of the resonator. Quality factor of the resonator is directly related to loss, and from those loss, based upon the theory, we can find out how many losses are the TLS losses and how many losses are non-TLS losses. So what we do, okay, based upon the 2 decades of experiments, the scientists know major losses at air or at different interfaces. Metal-air interfaces, metal substrate interfaces, and substrate-air interfaces. So basically, my area of research is I play with these interfaces and try to reduce, okay, the TLS losses. First, I check from where these losses are, and then we try to reduce it. So there is a 3 interfaces over there: metal-air, substrate-air, okay, and the metal substrate. So I play with these interfaces. So what we did first, okay, this is we looked at it, how many oxides are there. So this is the cross-sectional TM images, and you can see clearly there is a niobium oxides over there, and this is the XPS data. And then we study the silicon also, the cross-section, and we observe there is a lot of oxides over there. So, okay, just maybe 2, 3. And then we remove these oxides, okay, by wet etching. And by wet etching, we were able to remove these oxides, and we did the quality factor measurements, and we observed, okay, very clear improvement in the quality factor. So one thing is clear, these oxides, okay, are the host of the TLS. If you remove the oxides, you can improve the quality factor. We were able to improve the quality factor from 0.6 to 1 order of magnitude. And then what's the problem over here? Okay, if you expose the chip again to the environment, and that definitely we have to do it, then oxides regrow, and we lost, okay, the quality factor. So, so in this particular paper, we said, okay, oxides are the TLS host, remove them, you can improve the quality factor. But the problem is, this is not a sustained solution. So what I propose to sustain this, improvement, so I use the self-assembled monolayer. This specific type of molecules, it's well known, okay, developed by the George Whiteside in 1992. He proposed these molecules, okay, and these molecules are using it in chemistry in different areas very frequently. So I use these molecules, okay, after etching, I put these molecules, and I was able to have the sustained improvement in the quality factor of the coplanar waveguide resonators, or which is directly related to the coherence time. So there are a few slides over there. So these, okay, SAMs have been used, okay, to change the chemical properties of the surface, to change the work function, to change the dielectric constant. And in my case, when I did the quality factor, I put the SAMs over there at these interfaces. And when I put these SAMs, this is the XPS data, I was able to suppress the growth of the oxides. And the most importantly, over here, I observed a clear improvement in the coherence time of the qubit. So these self-assembled monolayer can improve the coherence time of the qubit, okay? Because you etch it, you remove the oxides, put these SAMs. So we test these samples even after 3 weeks also, and there is no presence of extra oxides over there. So now I would like to, so coherence time of the quantum circuits can be increased by removing the oxides, okay? But these oxides, okay, by etching, they regrow it. So this regrowth can be suppressed by putting the self-assembled monolayer. So, but self-assembled monolayer are contributing in the coherence time, still we don't know. Whether SAM itself, because we believe SAM suppress the oxide, but the SAM itself has a very interesting dielectric properties. Whether SAMs are contributing in the coherence time, yet we don't know. And finally, okay, I did all this work, okay, at KAUST, okay, and at UC Berkeley. But recently I started the same project, okay, with KAX, and I'm in touch with them for last January, and hopefully in summer, okay, we will be able to reproduce the same results here locally in the kingdom. Thank you.
Ladies and gentlemen, Please welcome to the stage our next speaker, Professor Philip Hammer.
Okay. All right, so it looks like it's not displaying quite right, but basically I'm talking about nanodiamonds. So nanodiamonds are quantum sensors. So you just heard about quantum computing. Well, quantum sensing is not quite so far along as that. It's maybe 15 years back. So what I'll show you is something at the very beginning. So next, how do we change? Okay, so you heard something about the nitrogen vacancy sensor. So this is the one that I'm mainly using. Nitrogen vacancy, think of a diamond lattice. Take out a carbon, you have a vacancy. Substitute the carbon for a nitrogen, you have a nitrogen vacancy. Now this color center is fluorescent. It has the unusual property that it spin polarizes when you excite it. And that spin polarization can be quite high, and it's at room temperature. However, the really important thing about this fluorescent center is the fact that its fluorescence depends on the spin state. There's about a 30% difference in fluorescence. If that difference were smaller, you would never have heard about it. Okay, it wouldn't have been useful. If that difference were bigger, it would be many more, you'd hear much more about it than you already hear. So it's on the border. All right, so basically it's a magnetometer. It's sensitive, it's a Zeeman shift, it's sensitive to magnetic fields. Okay, and so if you change magnetic field, you can see the levels split. Now the really useful thing about this magnetometer is that it can be quite small. We're able to see even one color center. The color center is the size of a molecule. Okay, so that's a very, very small color center. And so some of the early work is we put a nanocrystal on an atomic force microscope tip and scanned near a nanomagnet, and we saw nanoscale contours in the magnetic field. So this was many, many years ago. And so that's the first demonstration. So the really powerful application of this is very small nanoscale magnetic sensing. Okay, now I'm going to talk about a gradiometer. Why do you want a gradiometer? Okay, suppose you want to measure a magnetic field in something that's really small, like an ion channel in a neuron. Okay, of course we have patch clamp for measuring the voltage. But the way the voltage changes is because ions go through channels, and that's how the voltage changes. If you can measure the voltage directly or the current directly through the ion channel, then you would have a higher level of ability to see what's happening. Okay, so you can go ahead and calculate for a certain distance from the ion channel what the field is. And of course, you want to get as close as you can because the field decays. But you can't get too close because the ion channel is a protein. And so I just picked a level of about 5 nanometers. So you take a 5 nanometer sensor, which basically is a nanodiamond of about 5 nanometers size. You put it real close to the ion channel. And what you find is the sensitivity for current going through is on the order of basically 0.1 nanotesla. However, the sensitivity of the sensor is not quite that good. Okay, and so what do you do? Well, this problem was looked at by Leo Hohlenberg, and what he said is these ions that go through the channel have a nuclear spin. And you can see that easier than you can see the current. And so if you look at the nuclear spin noise, you get a much better number, and now it's easily sensed. Okay, so now suppose you want to set up an apparatus to do this. Well, first thing you find out, okay, here's the Biot-Savart current on the bottom, the nuclear spin on the top, the DC and the AC sensitivity of the sensor. But on the very top, you have laboratory noise. There's a lot of magnetic noise everywhere. Okay, and so and what do you do about this? Well, what you do is you don't sense the magnetic field. You sense the magnetic field gradient. The smaller the object, the bigger the gradient. Okay, and so now if we compare gradients, we see that in the laboratory, what's the biggest gradient? Well, you use a microscope objective to get close. If that was magnetic, you would get a gradient corresponding to that dark line. Well, now you see that you're well below all the things we're trying to measure. And so a gradiometer is definitely what you want to use, and that's what everybody uses when they want to detect something. And so you don't measure the field, you measure the field gradient. So how would you do that with quantum noise? Okay, so in a gradiometer, you measure a field at two locations, you subtract them. You subtract the fields, but the noises will not subtract if it's quantum noise. However, if you can do the subtraction before you make the measurement, then you get an enhancement. And that enhancement is similar to what you would get from, say, Heisenberg scaling or squeezing, with different mechanism, but similar advantage. Okay, and so now you can imagine a magnetometer that consists of two spins, and we'll put them in the singlet state. Okay, so that singlet state is not sensitive to any DC magnetic fields. However, a gradient can make it precess into the triplet. Okay, so it senses gradients, but not DC fields. And if you can arrange that the singlet is dark and the triplet is light, then you can sense very, very weak gradients. Okay, so how do you make this? Well, in the nitrogen vacancy, there's two ways to make a singlet state. One is with entanglement. It was demonstrated a long time ago that you can get entanglement between two of these color centers if they're separated by 10 nanometers. Okay, our nanodiamond is 5 nanometers, so there shouldn't be any trouble getting entanglement. Another approach is the direct excitation. This would be equivalent to sub-wavelength imaging. If we excite with a microwave, and we put a gradient in the microwave, we can separately excite these two spins that are very close together. And you work it out, and you find out if you have a 10 micron spacing, and you want to resolve two spins, you need about many thousands of Rabi oscillations. And so over on the right, you'll see there's many thousands of Rabi oscillations are possible. So that's another way to initiate this state. Okay, so the next question is, how do you make these? The first approach was to implant pairs of nitrogen. So if you implant a molecule, you have two nitrogens very close together, and you should, in principle, end up with two color centers very close together. The problem is it never worked. After 20 years, it didn't work. And the reason it didn't work is that because you implant these nitrogens, you get all these vacancies, you anneal it to make the nitrogen vacancy, but what happens is the vacancies stick to each other. And so the creation yield is very low, and so if you're trying to make a pair, it almost never happens. Okay, but that problem was recently solved. If you dope the diamond with phosphorus, oxygen, or sulfur, you can get very high conversion efficiencies because you make the vacancies repel. Okay, and that high conversion efficiency means you can now get pairs. And in fact, that's how the conversion efficiency was measured. So this is what we want to do. We want to take a nanodiamond that's doped with sulfur, and we want a single nitrogen in there, or a pair. Okay, and so what we did the first thing is we grew some nanodiamonds with a single nitrogen, and we implanted the silicon. Okay, how do you grow diamond? Okay, well, everyone thinks you need a big high-pressure chamber, or you need a plasma, or some expensive apparatus. But as you can see on the right, we just did a simple reflux with DMSO. It turns out that if you want to make a nanodiamond that's small, pretty much anything will work. You don't need any special apparatus. You just need to understand the chemistry. Okay, and so it actually is a fairly scalable thing. Okay, so this was the first evidence. This was actually done here at CAXT. And the idea was to take one of these nanodiamonds, which has sulfur and has a single nitrogen, implant silicons. Everywhere a silicon is implanted, we get a silicon vacancy, and we also get a single nitrogen vacancy. Okay, so it's very preliminary. Next thing we have to do is implant two nitrogens to see if we can get the pair. Okay, so to finish up, I just wanted to say we're starting a new project on graphene. And this involves another colleague of mine from Texas A&M, so there'll be two of us here. And of course, my collaborator here is Mosfer. Okay, so the idea of this program is to is to do exfoliation of graphene electrochemically, and not just to do it from graphite, but to do it from petroleum coke, because that's something that's not a high-value item, and usually you want to make it more valuable, or you want to make it more useful. Okay, and so this was the experiment that was done when my colleague visited. We exfoliated graphene from graphite, and you can see that it's not electronic grade, okay? But for those of you that know about graphene, there's electronic grade. It's very expensive. It's a single layer. It's very large sheets. But for a lot of applications, you don't need that. Okay, specifically for something like batteries, you need something that has good conductivity, so the sheets don't have to be as big. And so this is an example of something that was reasonable with graphite. Also, petroleum coke was used here at CAXT, and it's almost as good. And you can see that and it turns out the conductivity of this is high enough for the application of batteries. And so this is something that if we can scale this up, we can find a use for all that petroleum coke that's kind of being thrown away now. Okay, so I only had 10 minutes. I don't know if I used it all up, but the break comes after me, so I think I'll finish up here. So I talked about sensing with nitrogen vacancy centers. I didn't have time to tell you about the ST1, which is hopefully the replacement for the nitrogen vacancy that will work better. I told you about the advantage of a gradiometer, why you never want to sense magnetic fields. You only want to sense gradients of magnetic fields. Okay, and I told you a bit about the fabrication, how we fabricate these, and finally about the graphene production.
I would like to thank our distinguished speakers for these great talks, and I would like to invite them to the stage for a panel discussion. Please join us with the... Salim? So I know that we are a little bit behind the schedule. I know that we are behind schedule, but we have few questions, and we'll open the floor for the audience for questions. I will prepare. Okay. No, I can sit here. Yes. So, thank you. So, my first question to Steve. When Samsung announced the wall, the 100-inch TV, I remember it was in 2017, Las Vegas.
Yep.
A lot of people expected that the micro LED will dominate the market, especially for the displays. But I know that some of the major players like Apple canceled their project to replace their OLED with micro LED in their watches and cell phones. I'm not sure why. What's the obstacles? What's the reason for the not adopting the micro LED in the displays?
Yeah, the main reason that Apple and also Samsung have difficulties is cost. And cost is driven by yield. So when you're placing 12 million LEDs, you need 6/9 yield. And so that's a very difficult thing to do. It's not working?
Yeah.
Okay. Yeah, it's working. So yeah, so basically it comes down to yield. For 12 million, the mass transfer is just so low. The yield's not high enough, and so that reflects directly in the cost. So the cost of the micro LED technology has not dropped to the level that it's competitive with OLED for what I call direct view. So that's why people in the projection, that's augmented reality, is where most people are now focusing their researches for using micro LED for projection displays.
Okay. Do you think that because of the OLED becomes really high efficiency, and this is why not people switching to micro LED?
Well, the OLED's not high efficiency. That's why they want to switch to micro LED. We have better efficiency, but we can't beat them on cost. So
Okay.
until we make more cost-effective mass transfer or display technology,
Okay.
I think it's going to be relegated to augmented or virtual reality or glass-type display.
I see. I see. Professor Philip, I have one question. So beyond quantum technology, are there any other potential applications for engineered nano diamonds that you see?
Beyond quantum tunneling?
Yeah.
Oh, applications for sensors, you mean?
Yeah.
Well, okay, quantum tunneling is, I guess I don't think of that as much of a sensor. I think of that as something that's been around for a long time. So there are many types of quantum sensors. Usually when people say quantum sensing, they're talking about interferometers. Like in the LIGO, people wanted to improve sensitivity so they can measure gravity waves. And these are done with long pass and lasers and so on and so on. But my emphasis has been on nanoscale applications.
I see.
And so for me, the nitrogen vacancy works the best because of the temperature. So it's the only room temperature solid state quantum computer that's out there right now. I hope to replace it with something better, but I haven't been able, after 20 years, I haven't found anything better yet, so maybe soon. But yeah, I think for the types of applications I'm thinking about, where it has to be room temperature, it has to be quantum, I think that's the best.
I see. Thank you. Professor Dating, so where do you see the field of integrated silicon photonics with on-chip laser heading in the next 5 to 10 years? And do you think there is a breakthrough anticipated soon about this technology?
So actually, there's a lot of real progress recently. So in this year's OFC, so Intel announced that, based through our collaborations with universities, they have already made integrated quantum dot lasers with the silicon photonics in their foundries. So everything. This all in for our collaboration, it's like they provide the passive parts, and then we core into 4-inch wafers, and then we do the subsequent process in universities. But now they can do everything in their Intel, their own foundry line. So this is a very exciting thing, showing that okay, this technology is really possible to really transition into the industry to make products. Another very interesting thing is that, so currently the heterogeneous quantum dot lasers use SOI substrate with a thicker silicon, so around 400 to 500, which is much thicker than the standard 220 SOI substrate. But recently, a new company named Quintessent, they made a special structure that they can transmit the light from the 3.5 to silicon using the 220 SOI substrate. So, which means that this technology can not only be performed in Intel, they can also be accessible to all the other standard photonic foundries using the standard 220 SOI substrate. So I think this is very promising, showing that okay, our research efforts are now influence the industry, and they are actively trying to incorporate this technology in their foundry lines.
Got it. Thank you. Thank you very much. Professor Salim, I have one question. So what are the potential benefits of further reducing the quantum coherent losses in the superconducting circuit? And where do you see the field of research heading in the next few years?
Yes, as I mentioned in my talk, there are many different platforms for quantum computing, and different companies are working on different options, like optical, NV centers, ion trap. But the superconducting is one of the promising, and the Google and the IBM are using these as a major advantages is the fabrication. So whatever the number of the qubits you need, the technology is available to fabricate it. So there is no barrier in terms of fabrication. But the big barrier is the coherence time, the lifetime of the qubit. Low temperature, some people ask, you operate them at around 20 millikelvins. So that temperature is also an issue. Temperature is no more an issue because this dilation fridge the technology will be, okay, very soon it will be like a fridge in your home. Yes, it is. In 50s, there was a fridge is a big device. But this low temperature facility, we call it a fridge as well. This is not an issue. Only issue in the superconducting technology is the coherence time. Now people are working on a different architect. Okay, they are not integrating it. They are just simply putting it in a different dilution fridge, or in a fridge they are putting it at different distances. Different architects, they are working on it. IBM is already launched not in an open cloud, but to research it 1,000 qubit. Very soon, okay, few thousand qubits processor will be available. But it all depends upon the coherence time and some breakthrough or some material breakthrough. If there is an improvement in the coherence time, we are done with everything is ready. Okay, as I mentioned, theory is ready, circuit QED theory is very well known.
That's great.
Yeah. Only problem is the coherence time.
Thank you,
Yeah.
Professor. So the floor now is open for any question from the audience. Please, if you have any question for our speakers.
We got two over there.
Yeah, the microphone, please. So we'll have just only 2 or 3 questions because we're a little bit behind the schedule. And
yeah, hi, good morning. Thank you for your interesting talks and very good presentations you have shown. First, I have one question for Prof. Stephen and the other one for Prof. Philip. For Prof. Stephen, can you please comment on, you have shown very remarkable line width of your light blue laser. So can you please comment on the stabilization? How stable is these line width? Okay, have you measured the stabilization of your blue light lasers?
The blue laser, the line width. What's the line width? I couldn't catch it.
can you repeat the question, please?
Yeah, the stabilization of these line width of the blue light lasers.
Of the blue laser.
How stable are they?
The measurement technique?
No, the blue laser with the low line width. How stable it is, the measurement.
Oh, how stable?
Yeah.
Yeah, that was CW measurement, so it's very stable. There's very low noise on the laser. So it could be used now, but I will point out that Yenting showed a line width of 23 kilohertz or hertz. So we're nowhere near as good as gallium arsenide quantum dot lasers are. And so I think we need to do self-injection locking to make it more stable.
And the other question?
Yeah, my other question is for Professor Philip. So if you are working on graphene, and I know this material now is coming along with the industry, it's new. What do you think about the future of graphene material and the different applications for it?
Well, people are finding uses for it every day. I mean, we're looking into it for batteries, and that hasn't really been, there hasn't been too much emphasis on it yet. Concrete has been a little bit of emphasis, but scaling up is the big thing. So I think the main focus of the project here is how to scale it up to large quantities for these 2 applications.
Okay. Can we have one more question? One more question, please. Yeah, please. Yeah.
Stephen, you mentioned the attempts to grow the 3 colors, micro-LEDs on the same substrate. How practical this is in terms of getting, performance of the 3 colors on one substrate?
So yeah, we've already grown the 3 color, and so they're almost the same efficiency. When we've integrated all 3 colors, we got a little bit lower in the blue. It's about 30% instead of 50%. But another company, LumaLEDs in the Bay Area, has demonstrated 3 color as well now, monolithically grown with very good efficiency. So I'm pretty confident that we can get efficiencies above 50% for the blue, 25% for the green, and maybe 10% for the red.
The uniformity of the wafer?
Oh, the uniformity. Uniformity of the blue and green is very good. Uniformity of the red needs a lot of work. So the uniformity of the red's bad. Another approach taken, I think, by, I can't mention the company, they're using quantum dots for the red. And they use this, actually UV micro LEDs, and then they put the 3 colors on by quantum dot. That one has beautiful uniformity. So I actually think the quantum dot combined with micro LED will be the solution to the uniformity problem.
Great. Okay. Please thank with me our speakers again. And if you have any questions, you could ask them offline, please.
Ladies and gentlemen, and now let's move to the next session entitled Technological Advancements in Semiconductors Packaging. And our esteemed speaker now is Mr. Jing Wang. Please welcome on stage.
Okay, which one? Okay, that's it. Okay, so let me move back. Okay, how can I go backwards? Okay. Good morning, everyone. Yeah, it's my pleasure to present our work, advanced packaging of electronics as well as heterogeneous integration. So first, let me play a short movie, illustrate what is additive manufacturing, how it can be utilized for packaging or heterogeneous integration. This is our early work where we demonstrated a 2.4 gigahertz phase array, which is the subarray unit cell. And we put the subarray unit cell 4x4 of those 2x2 array into a quadcopter. The quadcopter was developed by the senior design group, which is basically the undergraduate student group. They were able to beamforming and transfer the video back to the source using the 2.4 gigahertz phase array. All additive manufactured, each of the unit cell take about 6 hours to produce. So it's not a fast time, but it's able to perform very well. So this was motivated by my early work, where the group developing the backscattering transponder. This is a device that's sort of transmitting the signal back with doubling the frequency first to minimize any potential interference, and also letting a sensor, in this case a vibration sensor, modulate the signal so you can carry the signal back at the same time. And the sensor is sort of getting a pretty decent range, up to about 30 meters distance, by staying totally passive. And this transmouser node requires us to make a 3D antenna. So one of the antenna receive the signal at 2.4, a dial-based doubler, narrow frequency, transmit the double frequency back. And you can see the vibration signal was captured. We also bury the device under a package, which is a ping pong ball, under the Vermont sound, and potentially, we can put it under the porous pavement on the street, continue to measure the vibration. So the goal is to make a 3D sensor and passive, and the trick to make it perform better is to actually design all the matching network to make sure you match to the fundamental, second harmonic, third harmonic, all the way up to fourth harmonic. So this frequency doubling device can work very efficiently for energy conversion. So it does have a conversion loss approaching about negative 10 dB by doubling the frequency, but still, because of the avoiding interference with direct frequency receiving at the same band, you're able to get a much better performance out of this sensor. Like I said, this is one of the first sensors of its kind as a passive backscattering sensor node, where you transmit the signal back passively after doubling the frequency. And we're testing this in an antenna chamber. The lesson learned at the time was we have to engineer an antenna in a sort of origami kind of form to make it 3D. End of the day, you can get a very uniform transfer pattern, radiation pattern-wise. So your sensor can be anywhere in the room. You don't have to know. Your transmission gain is about the same. So after learning that lessons, we continue to work into more additive manufacturing and packaging using additive manufacturing approach. This case, our motivation is to integrate a variety of different electronics. They can be RF electronic, digital electronics, or mixed signal circuits, all into a single package. And we also want to, throughout the time, developing something that is known as foundry design kits. This is some model library system design guideline you will have when you design microwave integrated circuits. Because we try to put circuit and package together in one design, you have to create your own system in terms of foundry design kits. Once you have that, you can have other designers using your additive manufacturing process and system and material to make their front end after they have such a design kit in their hand. So throughout the years, we're developing additive manufactured conformal antenna array. Many of them have embedded electronics inside. We started working with passive phase array, which have phase shifter, attenuator, and amplifier separately integrated into a 3D package. End of the day, they don't have to look at your traditional antenna. They can be a structured electronics, look like, for example, the belly part of the Scan Eagle airplane. They can help you to do the transmission as an integrated structured electronic device. One of our later work I will show later is to push this into the 5G high band. So this is a brief illustration of the system. Hopefully that movie can play. But that movie will show you how we do additive manufacturing by printing a structure and also the electronics interconnect and weir hole and other structure on top of it. I will talk a little bit more about the integration directly over the microwave monolithic integrated circuits, which we're able to replace the wire bonds and all the interconnect on a package by direct printing over your pick-and-place inserted circuits. We're able to do that up to 170 gigahertz. We're also developing model library in order to support you to understand better how to use this process. You can integrate circuits up to that frequency with very good RF performance. So this is some of our early work where we demonstrate packaging in the K-band, KO band, or X band of sort of antenna subcell element. Both of them have a patch antenna. One of them was printing from top side down. The other was printed from bottom side up. Another difference is toward the right-hand side, we introduced a cavity on the back of your antenna, so your front-to-back ratio can be greatly improved. We also play with porosity of the materials, so your antenna efficiency can be improved. So you can engineer material, system, and structure and shape to build those circuits to be most efficient for RF communication. So this is the measure performance for that second device. So as you see, we are able to show very minimal return loss across all the state of the phase. The phase stays stable across the X band. Radiation pattern was well engineered to meet our goal of front to back ratio above the 20 dB. We also achieve efficiency at around 80%, which is not the historical limit, but approaching it. So once we're able to do a flat unit cell, of course, we want to scale that up to a bigger array. In this case, we're looking at 8 by 8 doubly curved array. So you can design this and simulate its RF performance. Then you can do additive manufacturing using a 6x degree freedom printer directly printing such device. And with the device, you can do uplink and downlink as a communication device is phased array. With all of this done, you're able to achieve efficiency up to 87%, which is already including all the losses in your package. And also, we could put this as replacement part of that belly part, which is doubly curved. So you can have uplink, downlink through this passive phase array, but it's still passive. So we're moving towards building an active phase array. The first thing we explored was to minimize the electronic component count by using something that is known as the beamforming IC. The beamforming IC is already incorporated the capability of digitally control the phase and amplitude for all the 4 channels, and including receive and transmit in one package. The only trick is you're needing interface with switches and other circuits, and you may need to have advanced packaging technology to go down to the scale of at least 150 to 200 micron feature size in order to interface with all the pins of that package. We demonstrate we can do beam scanning using such a sensor, but more importantly, we learned even for such a beamforming IC at this X-band frequency, the thermal become a problem. At least thermal in the package become a challenge. You have to solve that along with EM design in order to achieve an optimal performance as you target for. So here's a few infrared image showing in our early design, instead of designing unique integrated heat dissipation structure like micro-channel, micro-pipes, we use traditional heat sink to see how that can help or hurt your performance. Obviously, introducing such kind of bulk heat sink can disturb some of your EM radiation performance. So later time, we changed that using some kind of microchannel in order to improve the performance, to make it more integrated. We also tested one of the packaged PA inside such a packaging technology. We're able to match real well between the simulated thermal performance and measured temperature. So carry forward, our latest work is pushing towards the 5G high band. We're targeting 26.5 gigahertz center frequency. We're building, again, a subarray, which is 2x2 antenna array. This case, in order to achieve a best compromise and balance between the EM and thermal performance, we create a periodical structure under each of the patch antenna. We use unique heat dissipation structure embedded in each of the structure in order to spread the heat. And at a later stage, we can also introduce new materials such as graphene to spread the heat at the corresponding layers. And graphene material we developed in our lab has shown thermal conductivity 3 times higher than the copper for the implant thermal dissipation. So it will give you better performance while also take care of the thermal management problem while introducing very minimal complexity into your package. And this is sort of demonstrated the measured performance of the phase and amplitude control by this package. This is the package of the unit cell, 2x2 unit cell subarray as compared to the size of my hand. And this is the scan performance of such a device. By scanning, basically the scanning performance is not optimal because it's only having 2 elements in the scanning directions. As we're scaling up this device into a bigger tile, it's going to give you even better performance. So this is to show such a device measured on a stage inside antenna chamber that we carry out at our university. This is to show how the temperature measured using infrared camera that is also later on calibrated against embedded sensor onto such a circuit. So you can be correctly model matched with your manufacturer package in order to give you thermal management details such as the temperature control and feedback. Furthermore, about that temperature control and feedback, comparing the infrared temperature where you have a 35 degree, the read temperature from this SPI channel is around the same temperature range, 40 degrees C. The difference might be due to the emissivity issue related to the infrared camera. So you typically need to calibrate it with the thermocouple and actual thermal sensor. There's a built-in thermal sensor on this beamforming IC package that we used for this purpose. So once we're able to demonstrate, we can package, already packaged pretty advanced circuits that have many, many leads. Another direction we try to push is to use the same technology simultaneously take care of heterogeneous integration of naked and packaged dies. In this case, you're looking at one such a die, which is in the right color. We can, this is a movie, by the way, if they can play. If the movie plays, you'll see we print a housing on top of your integrated circuits with all the interconnect and the feeding network. And this housing on top is like a pyramid, encapsulate your sensor against the liquid environment in this case. This is that package. You can entirely seal the sensor around from the environment. You can stacking up from this to make your sensor. At a later stage, we're using this kind of technology to put a lens on top of antenna array. So you can further improve the radiation efficiency by doing that. You can change the aperture efficiency by engineering that lens using some pretty complicated design algorithms. Okay, so we also, in this work, demonstrated one of the, at the time, record low loss for integrated interconnect directly printed using different structure. We compare coplanar waveguide, grounded coplanar waveguide. We look at the reflection coefficient. We're also testing them all the way in terms of reliability up to 250 gigahertz. So those circuits shows the record performance comparing to other printing technology, flexible electronic technology out there. We're able to get to pretty low loss, as you can see, up to the millimeter wave frequency. Our target band for these circuits is to operate between 80 and 100 gigahertz. They're able to achieve such a performance as you see on this plot. So once we compare with all the prior work in the similar area, I don't know, the laser doesn't show, you can see our loss performance in terms of dB per millimeter length is quite comparable. So we're really on the top in that table that you can see over there. Using this laser-enhanced direct print additive manufacturing technology, we're able to make circuit perform with very, very minimal loss per unit length. We're able to integrate them directly with integrated circuits in a single printed package in the form of heterogeneous integration. So this is a demonstration of us trying to put one of the power amplifier IC alongside of a low noise amplifier IC to make a transmitter receiver all printed directly onto a plastic interposer. So this dipole antenna and this dipole antenna can communicate to each other through such a printed package. Similar to your micromachining technique or the technique you make to build transistors, we're able to do the same thing by first putting a ground plane, leaving a cavity for the ICs, putting all the weir holes, refueling the weir holes, putting all the RF transmission line interconnect at probe ports, putting the bypass capacitor along with pick and place, inserting those ICs into your heterogeneous integrated package. End of the day, we're getting such a package. Now we want to see how they perform. They actually perform pretty well. So by comparing direct probing of your circuit without the package versus putting the package on top of your circuit to give you our easy to interface to port, you're seeing about additional loss of 1 to 2 dBs across the band of interest. We're operating between 80 and 95 gigahertz for this kind of transmitter receiver directly printed onto a plastic package. And then the interconnect loss, the interconnect between your IC and the surrounding package is de-embedded to be about 0.5 dB, which is amazingly low considering very, very high frequency we're operating at. And because of the modeling effort we have, as we talked about before, we can design this to have a pretty good return loss to match with the impedance of needed. So this is a demonstration of those circuits. We put in other demonstration, we put the low noise amplifier and filter together. We're comparing our loss in terms of loss between the chip and the surrounding package. We're showing a result that is comparable or lower to other people at 80 gigahertz range or the millimeter wave frequency range. So as a group, we also work on developing newer materials. And for example, some of those technology that we have protected with the IP and patent might be carried forward as a startup company potentially over here. So we produced material that we can use for direct additive manufacture, a dielectric waveguide which is this piece of devices, that can operate at up to 170 gigahertz. They're showing much lower loss as compared to most of the metal transmission lines. And in other cases, when we need to enhance the efficiency of the radiation device, such as antenna or antenna array, we can put an array of designed lens on top of them in order to change their scanning performance and their gain and their efficiency. And also, we produce material in-house that can generate permittivity up to about 12 at frequency even up to about 170 gigahertz that we recently tested. So as a highlight of this work, I now want to show a couple of bonus slides, which shows some of my students graduated from my group that actually joined CAST as professors. So Adnan, some of you might know him. Abdul, they're a little shy, they're staying in the background, but they're one of my very, very excellent graduate students out of my 20 PhD graduate. They're as professors. And if this movie plays, you can see this is actually that printer. When I talk about printer, it's not a tiny printer on your desk. It's a printer that takes us to remove a window from our neighbor's lab to be delivered because our elevator is just not big enough for it, right? So it's $1 million printer, but it can do additive manufacturing using it, almost directly replacing many things you can do or you need to do in the clean room. You don't have to do lithography. You don't have to go away from one single platform. You can make your devices or the entire package using this one system. This is just a quick highlight of Adnan. He didn't work on packaging. His work is mostly related to microwave acoustic. We make acoustic devices in-house designed, microwave fabricated. In his case, he introduced both piezoelectric transducer and capacitive transducer in one device. So his device can show outstanding isolation between the ports all the way to the system limit because he implemented this kind of novel concept. Abdur, also now working at CAST, his project was to introduce photonic crystal, similar to the photonic crystal concept. You introduce a band gap, but in the acoustic domain. In this case, you can improve the quality factor drastically by using such a technology. He's here at CAST as a professor as well. Last but not the least, my department chair sent me here to also advertise the work related to our newly developed online STEM program. And this program basically can be taken entirely online. And then as a student here, if you're interested, you can take a brochure from me and or from my former students. Then you can enroll into this class online to get a STEM certificate, mostly related to the semiconductor manufacturing and semiconductor device engineering. With that, I want to close out. Thank you.
Ladies and gentlemen, please welcome to the stage our next speaker, Professor Atif Shamim.
Hello. I can still say good morning. So I'm going to be talking about some of the packaging work we do and focus on enhanced functionality and affordability and higher level of integrations. So there are a lot of semiconductor people here, and we often talk about the Moore's law, where you are doubling the transistors every year. So if you look at this over the period of years, you have been putting more and more transistors, now going to billions of transistors on a chip. But what we do not discuss is this is only 10% of the system. So ICs typically are only 10% of the system. The rest of the 90% of the systems are interconnects, passives, power sources, and others. So the system on package concept, which I'm showing you here, also came out with the Packaging Research Center from Georgia Tech a couple of decades ago, is basically dealing with that 90% of the system, how to miniaturize that. So bringing those big lumped components or discrete components to kind of thin film technologies and try to miniaturize that. So you could see on the right side of the graph that we try to bring those to the millimeter wave or millimeter or nanometer scales. Now, just for the people who are not very familiar with this, when you have a piece of silicon, it's a bare die. It's called a bare die. This needs to be packaged. So in a system, you have many chips or many ICs. So each IC is packaged separately, and then they go onto a system package. So for example, if you look at your phones or laptops, if you open those up, you'll see a motherboard, and you see a lot of ICs. So on top of that, you have a system package, but the individual ICs are also packaged. Each of this package costs money and takes space, but they do not perform any function. So there's a huge packaging industry, and there's a lot of money spent on it, but they do not perform any function. So the idea behind system on packages, can we make the package functional? Can this packaging, because it's taking up space and it's costing us money, so can we make it functional, right? So this is a concept where you see that you could basically, I don't know whether you could see my laser, you could see that the IC is represented by these red colors. These ICs are in a package, but this package is comprised of thin films. And these thin films can have all your passive components embedded, like your interconnects, inductors, capacitors, antennas, filters, which have to be integrated with your IC. And I'm kind of focused here on the wireless or the RF kind of front end. And the technologies which are typically being used here on this side I can show is low temperature co-fired ceramics. These are a multi-layer kind of medium where you could actually have up to 100 layers and you could embed like these thin film components there. Also on the organic side, there is LCP, which is the liquid crystal polymers. They can also be multi-layer platforms. Now I'm going to show you a few examples because I only have like 10, 12 minutes. So I'm going to just show you a few examples of how this package can be made functional and can be useful to be part of the system. Here I'm showing you a front end of an automotive radar. This work we did many years ago. And you could see that the IC is here at the bottom here. This is a package, and you have a transmission line which is going through a ground plane connecting to the antenna element, which is a wideband kind of fractal antenna. Then you have an array of these elements, and you have certain, all of this is realized in a package. And then we integrated a lens within the package. So this IC, so the job of this package is typically just to protect the IC from the environment, but here, this package not only have all the interconnects, the feed line, the antenna array, and also a lens integrated in the package. So this is the fabricated module. You see one of the arrays, the feed network. Rest of the things you cannot see because they're all embedded in those multi-layer substrates. And then this is the lens. You see a Fresnel lens doing the phase corrections and the radiation pattern, all that. I don't know whether you guys can see this, the end of this table because of these sofas over there. But what I show here is that because of this integration, high level of integration in this package, we were able to reduce the size and the thickness of this radar module by 80%. And we also, I cannot do a cost analysis, but we also reduce the cost because you don't need any extra substrate for the antenna arrays and the lens. It's all done in the package. So not only compactness, high level of integration, but much more enhanced functionality. This is, again, example of a GPS filter, which is, if you look at this, these are capacitors and inductors. These capacitors are like interdigitated in a fashion not only horizontally, but also vertically. Because we have these multi-layer platform, so we can have these horizontal and vertical kind of layers. So all of these combine, and we do the design of this filter. I'm not going to go into the details, because of lack of the time, but this is 4 layers in the organic version, which is the liquid crystal polymer. And this is the fabricated version, and this was, at that point of time, one of the smallest GPS filter with very good performance. Again, this is realized in the package of the GPS IC. This is a work which we did with IBM, TJ Watson Center, USA, where this is an IBM process where we designed, these are the circuit layers you could see here. All the circuits are here. And what we did was that we had this package which is also from a high resistivity silicon. So this is all silicon. So you have your silicon chip which has all the circuits and the antenna layers. And then you have the package which is the high resistivity package, and we integrated in one of the package layers a ring lens, and because of that, this is the fabricated picture of that ring lens, only not the bottom part, and we were able to enhance the bandwidth, efficiency considerably of these antenna elements on the silicon substrate. So this is an example of a highly integrated system, all silicon based. Now this is again another CMOS chip, 71 gigahertz. The previous one which I showed was 94 gigahertz. So 71 gigahertz chip, the circuits, and there's an on-chip antenna, and this chip needs to be packaged, and we did the package in a way that, in this case, is very similar to what Jing was showing, is an additively manufactured 3D printed package, which is in the form of Fresnel lens, and you see these are 3D printed lens, and because of this, from a standalone antenna on chip, which was on the chip, and we had like a negative gains, when we integrated this Fresnel lens and the superstrate, the package, we were able to increase the performance by almost 20 dBs, which is considerable. And now, I've talked about the package and enhanced functionality. One last thing which I want to talk about is, can we add control to them? So we made the package functional, so the package is now part of the system and is helping us. But can we control the components which are realized in this package? So there's some work which we did where we added magnetic particles in the package. So mixed ceramics with the magnetic particles, so the package has now magnetic properties. So this means if I pass a DC magnetic field or a DC current to create a magnetic field, I can change the properties of this package, which means the components which I've realized in this, I can control them. I can control their frequency, I can control the radiation patterns, I can control the polarizations, I can do a lot of stuff, which is very much required in today's telecommunication, because there are multiple bands, and because of the frequency spectrum, congestion, you want to move in different bands and all that. So, but typically what people do when they do magnetic kind of biasing, they have these big electromagnets. And these big electromagnets are not very, very integrable, into the small platforms I'm talking about. So they will have typically a big magnet, and you will have your module, and they pass this magnetic field, but you cannot integrate this magnetic field. So what we did was we came up with this concept of windings. These windings are kind of embedded within the package. So you pass a DC current, and these windings, because of DC current, will produce a DC magnetic field in the upward direction, and it will basically kind of magnetize the top package. Now, you don't need any separate magnets. This is highly integrated, and also because we do not lose any magnetic fields in the air, we were able to reduce the bias required by 90%. So again, I'm going to show you some examples of this kind of work. So this is just a typical patch antenna. We have a ground plane, but you see the windings at the bottom. So the smart thing here is the high frequency fields, they cannot go beyond the ground plane. But the DC magnetic fields can go beyond this ground plane. So we kind of isolate them, but we're still able to magnetize. And what we are able to do, this is the fabricated module. You cannot see, this is the picture of the winding before, but this is the complete module, and the winding is completely embedded in it. So you cannot see it. And what we could do is you could see that we are able to tune the frequency by 1 gigahertz. So I pass current through this winding, and whatever frequency I want, I can make this antenna to work at multiple frequencies, or I can do continuous frequency tuning. This is example of a filter. Again, you could see these multi-layer windings, and you see the filter on top, and you could make this filter to work at different frequencies. This is very cool. This is a phased array, and you could see that there is a phase shifter which is embedded within this. So this is a waveguide. It's a substrate integrated waveguide. And underneath I have a winding. I pass the DC current and I create this magnetic field which controls the speed of the wave going in. So I can control the phase in this part. See these are the phase shifters. And then I have these slot array antennas in the same module. So because I can control the phase, I can beam scan. So this is what is required for all the radars, automotive radars. You can scan the beam, but in a very small factor. Typically, these phase shifters are very expensive, especially when you go to millimeter waves, and you need to integrate them. Here, the phase shifters are like readily integrated into the module. This is again the fabricated module. You could only see the top part. This is actually more than 16 layers, which you see at the bottom. And we have phase shifters, we have antenna elements, all integrated in that small module. And you could see the beam scanning, bypassing the currents. Okay, so with this, I stop here. I just want to tell you that System on Package is an emerging platform where the package becomes part of the system and it is functional. It provides affordability, it provides enhanced functionality, and the antenna and package, some of the antenna and package work which I tell you is actually very much liked by the industry. And I know companies like Sony Ericsson, Samsung already have these antenna and package implemented in their next generation mobile phones. So this concept is now becoming real because people want to use packaging for their parts. And the other part which I told you, that adding control, now you could reconfigure your packaging elements. And so new packaging approaches, as also Jing showed, additive manufacturing, high-risk silicon, can be used for packaging which is not being used. Thank you so much for your attention.
Ladies and gentlemen, please welcome to the stage our next speaker, Professor Muhammad Amir.
Hi, everybody. So today I'm going to be discussing something a little bit different than what we had in the previous talks. Basically, I'll be discussing electronics and how they're related to artificial intelligence and machine learning. So let's begin by exploring the industry, the semiconductor industry landscape. You can see here from this figure, or these two figures, that the acquisition and merger for a lot of semiconductor companies is taking a rise for the past, I would say, 5 years. Actually started in 2016 and started to grow significantly. And this significant growth actually happened because of the need for AI, especially with the large amount of computing that is happening in the machine learning algorithm. The electronics is not keeping up with this, and we're going to talk about this later. But here, the market, the snapshot for the artificial intelligence market is actually significantly growing. And with that growth, you've got two different types of companies. You've got the software-based companies that can do algorithms such as, of course, OpenAI. You've got the Google, IBM. You've got also Amazon, as well as X. Hardware-based artificial intelligence, on the other hand, is also taking a huge rise in this entire market. You've got NVIDIA, which is #1 right now when it comes to artificial intelligence hardware, and you've got Cerebras, Intel, AMD, and RAIN. There's a lot of applications where these AI actually taking place. You've got mining, robotics, fintech, biotech, and deep space. In our case, we're actually going to be focusing on robotics and deep space for intelligent machine vision, as well as emerging technologies for deep space. Now let's take a look what's really happening with the artificial intelligence itself. You can see here from when OpenAI or ChatGPT came along, the amount of training of AI has significantly doubled. Here you can see the trend for the past, I would say, decades is almost okay, and then it started to double within 2015 or 2016. So this basically tells you that AI is hungry for a lot of things. First one is hungry for electrical power dissipation. It's hungry for thermal power generation, and it requires a lot of memory. And if you look at this graph right here, it's showing you the memory wall, where the scaling of the transistor keeps on increasing, but the bandwidth for the interconnect is not increasing as much as the CPU, which gives you this memory wall that it prevents you from doing the neural network in a more proficient way. And you also get the thermal design management. Thermal design is also another aspect that you actually need to take care of when you do advanced packaging. Unfortunately, for the past years, there's not a lot of thermal power designs that can efficiently produce electronics that can be used for AI. Also, one thing you need to notice here is the Moore's law and the current trend. Ideally, it's supposed to be the cyan-looking line, but unfortunately, it's not following this trend. It's a little bit lagging, and also when you do the scaling of these transistors, as I mentioned before, there's a lot of power scaling. It's actually increasing exponentially. But with this all different increase, unfortunately, the computing power is reaching a threshold. And this is causing a huge problem here with the AI electronics. So with that in mind, let's take a look at the landscape of the advanced packaging itself. Packaging has been also on the rise. It depends on the input and output, and also on the pitch size of these electronics. In the beginning, it was just a simple packaging, and then it went to a flip chip and so on. And eventually, it reached a hybrid bonding. This is like the state of the art right now. Hybrid bonding has been actually looked at recently, especially with the small pitch size. And you've got IRIA as a company that can do this type of hybrid bonding. You can see the process here when you have two different wafers, and they actually being bonded together. Or you could have a dielet or a chiplet that can be bonded into a wafer. Advanced packaging can actually include 2.5 chiplet packaging, as you can see here, the planar system-on-a-chip integration, and 3D heterogeneous integrations. Basically, these three different packaging systems, I'll be discussing them in more details in the next slides. What I want to mention here is we want to integrate sensor, we want to integrate electronics, we want to integrate also high-level computing, all on a simple package that can be used by the consumer or the client. Now, let's take a look at this. Do we have an architectural problem in the first place that could actually contribute to this, improving the packaging or not? So packaging is basically a real estate problem. We're talking about real estate because we want to shrink the area, and so that we can use it for other things. This is the real estate. And also, we want to increase the performance or even improving on that performance. So we're going to have to look at the digital technologies that is currently being used, or the architecture of the digital technologies. So, and on all these different AI applications that uses sensors, the sensor basically will communicate with the analog to digital converter, and the analog to digital converter will communicate with the memory storage, and that memory storage will actually communicate with the CPU to do the computing, and so on. So this entire process has a couple of problems. One of these shortcomings is basically the latency. Latency is a huge problem for this. Also the bandwidth between the interconnect and the different units you have here. So this is probably people are familiar with the Van Neumann architecture. This is not really a proficient way of doing this. So Well, we want to do actually to create something much better than this. But again, when we take a look at, for example, at the Google Tensor Processing Unit, they have very complicated processes that goes into this. And even when you do intelligent machine vision for AI applications, you get a lot of circuits, very complicated circuits. So these complicated circuits using silicon technologies will actually create complicated fabrication and therefore higher costs. So it's not really optimized for AI applications. So what we're actually looking for is more into the neural network or analog computing that can be integrated with digital computing. So how could you do this? Basically, you use the neural network concept where you have synapse processes, just like the neurons in your body. And basically, the sensor will be connected to an array of memories that can actually do the analog computing. So there's been a lot of research that is concentrated on this type of different memory computing. You've got memoristic computing, you've got non-volatile memory computing or spintronics, and I think the next talk will actually talk about this type of memories, specifically in the non-volatile memory and spintronics. So you can actually integrate these type of sensors with all these memories and you can do the computing. Now, this can be demonstrated using our sensor. This is actually a biosensor that we have created for an array of sensors that can detect different diseases right away. We're using something called electronic ELISA. Electronic ELISA is a new process that you could use a field effect transistor to detect different diseases. And the way you do it is just you have a receptor or an antibody that is anchored to the indium oxide transistor. And you can easily detect, for example, different diseases depending on this antibody and the antigen that is being in the sample. So we have demonstrated this before for COVID-19 when COVID was a thing in the past. And then we also demonstrated not electronic ELISA, but electrochemical reaction using the sensor. And we were able to get one of the highest sensitive sensors to date for this type of glucose sensor. So in order to do this, the best way to do it is using near sensor computing for this type of a biosensor. You can see here it's actually connected to a couple of memory arrays. And basically the detection, if you want to do the precision medicine aspect, basically you want to detect cholesterol, you want to detect glucose, you want to detect other diseases as well. You can do it all on the same chip. And that's what actually we're working on here. And the way you integrate it is basically you have the sensor on the top, and then you've got the memory array on the bottom, and finally it's integrated with the CMOS digital platform. Another thing we're actually very interested in is something called in-sensor computing. What I showed you before is called near-sensor computing. Near-sensor computing is pretty much famous in the field of AI, analog AI. But in-sensor, this is a new concept. Basically, the sensor itself has to be should actually exhibit a photoconductivity that it can be tunable. So the sensor can do the computing itself and then send the computing right away into the digital platform. And there's actually, you can see here, this is an array of sensors that is actually doing the computing. For example, I'm using an optical sensor that can detect light, for example, or detect a specific object in this case. There are some specific requirements for this. The first requirement, it has to be reconfigurable using high responsivity. So, and this responsivity, as I mentioned to you, it has to be tunable. So what do I mean by tunable? I mean it has to be tunable by an external voltage, such as a gate voltage. I'm not saying it has to be tunable using the wavelength, because a lot of sensors can be tuned by wavelength, but it cannot be really tuned by a gate voltage for a specific wavelength. And it has to be also white, it can actually detect white light. So identifying this type of optical sensor is really hard. But here, I think the slide is a little bit messed up. Well, we actually demonstrated here is a photodetector that can actually have a tunable photoresponsivity with a gate voltage. And you can see the responsivity is actually pretty high, actually, when we actually do the benchmarking here compared to the other technologies out there. You can see using MOS2 and WS2 as a junction, it can actually exhibit a very high responsivity compared to other devices or other technologies that can do the in-sensor computing. and also exhibit a very nice tunability for the photoconductivity. The other thing about this photodetector that can do in-sensor computing, it exhibits a very low power dissipation compared to other technologies that actually being implemented for near sensor computing or even in-sensor computing. So to do this, we do the AI packaging, as I mentioned to you before. The sensor is connected to the digital platform and all of it on the actual substrate. This type of sensor can do low-level processing, high-level processing by classifying different objects or even feature extraction. So we can talk about this more in details in the future if you're interested. So in summary, semiconductor packaging using silicon base is reaching a bottleneck or reaching a barrier for this. Advanced packaging for AI hardware will require more architectural thinking. So the in-sensor and near-sensor computing, you need to rethink the architecture of the actual packaging so that you can have a better packaging or with increased performance and a low power. And I would like to thank the team for the support, the entire team from CAXT, especially the clean room, and also would like to thank Dr. Thaman and his group for the support in the clean room, and I'll be happy to answer any of your questions after this session. Thank you.
Ladies and gentlemen, please welcome to the stage the moderator of the Q&A session, Suhaib Fahmi, and the respected speakers.
Okay, so we're on a very tight budget because we're a bit over. So I will throw an initial question to our panelists. If anyone will take one question from the audience because we're on a tight schedule. So if anyone has a question, if they can get ready with a microphone. And my initial question is regarding what you see as potentially unique opportunities for packaging industry here in Saudi Arabia, considering the types of systems we might be building and the contexts like NEOM and other giga projects here, what you think could be the packaging opportunities. And I'll let each of the speakers give us a perspective.
I guess I will start. I think there's many of the design aspect that can be carried out, modeling of the package, which today is not widely available. For ICs, you have process design rules and process design kits. For the packaging, you don't have a standardized method to do that. It will be very beneficial to develop one. The whole industry is going to benefit from that. In addition, maybe some packaging-related materials, especially if you think about introducing something with unique feature and properties, such as thermal conductivity, something that shows extremely excellent ferrite properties, for example, that can be very beneficial for the whole packaging society. It may not take more than a wet lab and a clean room to develop those technologies. And the turnaround time is quicker.
That's great. Thank you. Thank you, Professor Wang. Maybe Professor Shamim can give us his perspective.
Yeah. So I can just add to what Jing said. I think like we talk about the ICs of two models, which is one is actually the foundry and the other is a fabless model, which is design model. I think the same could be applied to the packaging industry because one is the manufacturing, but there's a lot on the design side which can be done. And you've seen some of the stuff which we have been doing here. I know there's a lot of work going on with the NEOM on sensors, IoT sensors, and we saw how the integration of sensors with the circuits is a challenge. So I think on the design side is something which can be started right away for the Saudi Arabia, which is like a fabless model, you know. But then later on, of course, Saudi Arabia is also trying to do a lot on the manufacturing side. So packaging is essential part, and if we can set up a manufacturing, especially if we can couple this with additive manufacturing, you know, so that will be, I think, a kind of niche area for Saudi Arabia to get in. That's my point of view.
That's great. Thank you. Professor Amir, give us your perspective.
I would say I'm just going to reiterate what they mentioned. There's a lot of opportunities out there that you can do for advanced packaging, especially in advanced packaging area. You've got the hybrid bonding that I just mentioned earlier. This is actually a hot topic right now, especially with the new state-of-the-art, how you can integrate, for example, 3-5 materials on silicon for optical communications, for optical applications as well. So hybrid bonding is a very important topic that I think the kingdom can actually flourish in it. One thing you could also add is the chiplet design. Chiplet design is another important aspect of how you can shrink the size, and so you can increase the real estate area of the packaging. These two main things I think can be very high priority for the future of advanced packaging in the kingdom.
That's great. So I think those points are quite important for us to be thinking about across the whole system stack, and the idea of chiplets and computer architecture, and then the systems that we're building. I think that's a great perspective. So we'll take one question from the audience, if there is one. Make it a good one, because it's just the one. And I think we have someone.
So I don't know if it's a good question, but I'll give it a shot anyway. So my question is, Dr. Amir, in your presentation, you talked about the biosensors, and obviously we are already seeing 3D, many layers, many substrates. Are there actual chips in the market right now which also have these biosensors along with, memory stack and computing all in one?
Yeah, so the question is basically if there's any devices or products in the market that can have the biosensor with the memory integrated together, correct? Yeah. So I don't think so. This is emerging. This entire thing is emerging. The near sensor compute. This is called near sensor computing. Near sensor computing is still emerging. A lot of the near sensing computing that has been applied has been to a completely different application, not biosensing. I would say machine vision is one of these near sensor computing that has been really applied into. But in terms of biosensing, it's still emerging. I think there's a problem with the sensor itself inherently on how you could get almost a uniform types of biosensors that can detect all different types of things that you want. For example, you want one for glucose, you want one for cholesterol, for example, and one for example pressure or whatever. All of them should be integrated on the same memory device. So this is the challenge here, is actually the sensor itself and then the integration of these sensors into the memory. So I don't think, based on my knowledge, there is any product out there that's been implemented for this. It's still emerging.
When are they expected? Do you think that some of the big players that are already working on it? Is there a timeline? Because obviously with this, the AI and all that you talked about in your presentation, these would be very critical. But yeah,
I think the roadmap for this, or the landscape for this, there's a lot of efforts in terms of R&D. When it comes to the precision medicine or basically detection using AI. So still not on, still within the R&D stage. It did not reach that commercial stage yet.
Okay. So unfortunately, we are so behind that we've been asked to keep the panel short. I'm sure the speakers will be happy to engage on the sidelines, but I hope you'll join me in thanking them one more time for their insightful contributions, and hopefully we can move on with the program as well. Thank you.
Ladies and gentlemen, we will have now a 15-minute coffee break. Please enjoy your time. Ladies and gentlemen, the coffee break is over. Please return to your seats as we will resume our sessions. Thank you. Ladies and gentlemen, the coffee break is over. Please return to your seats as we will resume our sessions. Thank you.
Ladies and gentlemen, welcome one more time. And now we'll explore the transformative potential of integrated sensors in a session entitled Integrated Sensors to Empower IoT and Beyond. Please help me welcome our speaker, Mr. Kang Wang.
So, very good afternoon. You see, they have to wait it until it's the afternoon. And that's the reason for me to say good afternoon to you. So my name is Ken Wang. I'm from UCLA. And I wanted to show you, I had to click these things. Oh, what happened? Where's my first slide? Oh, this is the first slide. Sorry, they changed the color. So this talk is a soft talk of hardwares for AI. So I will adapt with the name. Started from, for example, CMOS to what's beyond AI. That's what I'd like to talk to you about it. As I said, I came from UCLA, and I was supposed to have a beautiful UCLA picture show that Los Angeles actually can be very beautiful. And in fact, Los Angeles is home of Hollywood. And Hollywood sometimes ahead, particularly in AI, and I'll show you what I meant by that. So this work, in part, is a collaboration between UCLA, USC, and CAST. And this we're very CAST here. So I'd like to share with you my thought about this. So if you look at today's computer, let it be phone, let it be pads, let it be any computer that you may have had, is that it's nothing but based on so-called von Neumann computer, which actually fundamental principle is called Turing machine. The Turing machine is based on one thing at a time. You read from the tape, that's the memory, and then you execute it. So you do one at a time, and therefore after that you dissipate energy to your bus. As a result of that, you want more function. Mr. Moore gave you more function by increasing number of transistors per unit area. That's why we call that two-dimensional scaling. Today, we say, well, two-dimension scaling is almost approaching the limit. So what do? We go three-dimension. But that is not going to be as good as two-dimension. And this is the problem, right? So suppose that you have this, I did a quick estimate that if I have a 10 centimeter by 10 centimeter chips and scale down to all the way to atomic scale, how many transistors can one have? I estimated roughly 10 to the 15. 10 to the 15, I see over over there. You see, they changed my slide a little bit. Now, 10 to the 15, for those of you very good in math, that is exactly 2 to the 50. So 2 to the 50, right? Now, if I estimate that the energy consumption based on dynamics energy dissipation, which is energy times frequency, as I try to look at the screen here. Let me do it this way. I can see the screen myself from here. That's what they have. So that is huge, 100 megawatts. Today's supercomputer, like a Summit, it dissipates 10 megawatts, costs $200 million at a 200 petaflops speed. Now, this is not going to go better than that in the scaling, so it's going to stop. So what do? Even worse, there's a 100,000 time latency between, remember, Turing machine is read from memory and execute it. That is going to, we do more integration, the latency increases and the power dissipation increases by 1,000 to 10,000 times. Hence, we like to do this computing, put them together. That's called compute in memory. And you heard talk last session about the compute in memory already, and this is what you have here. Put as many memory as possible as close to CPU. And, oops, this change a little bit here. So how can we do better? That's how neuromorphics comes in. So neuromorphics has, say, human brain is 80 gig neuron. Neuron is like a logics, right? And then you have 10 to the 15 or 14 synapse. Synapse is like memories. So you put them together at a row, and then you feed many memory to one neuron. So you have more function now. Say you have 20 or 50 synapse fit into neuron. That's 50 times more functionality in that sense. as a result of that, by the way, this is based on the so-called integrate and fire model of Huxley and the original 1960 or so. That's a model. We haven't changed that much yet. So as a result of that, we think a neuromorphic can have a more functionality, therefore increase the reduce energy, increase the performance. That's what you have. Now, obviously, this is like 50 people talk to me, so I increase functionality. Better yet, is everybody, 50 people, all talk at the same time, coherently. And that would be, you have power of 2 to the 50 people. That's the power of quantum computing. Scale exponentially. So that will be going to take it from Moore's law to a new law of quantum. But of course, that has its own challenge. In the interest of time, I will not go into detail on that. But rather, I will talk about why we do neuromorphic and AI. And I want to use one example, which spintronics could be used any example to illustrate that you could achieve extremely low power, and you can do stochastic computing statistically, and then it will come back to say, hey, what is the history of AI? What's today? And for example, ChatGPT and other generative process, and what's beyond. And if I have time, I dab with what are the challenges of the so-called integration with the CMOS. It's called back-end of 9 integration. Now, neuromorphically speaking, you look at neuron, this is the neuron, and there's a synapse that you can see here, but that is not static. Our neural models in the AI, actually in the neuromorphic, is actually static. It is actually dynamics. So it has a whole bunch of dynamic behavior, which we have not taken advantage of them yet. So if you look at the NVIDIA system and say the Healy of Intel system, they're actually still 10,000 to 1,000 times worse in energy computing, in energy dissipation. So can we do better than that? That's what we're looking for. So now, memory is everything, because I mentioned to you in this model of you need a lot more memory, 10 to the 6 million times more memory than logic circuits. So that's the reason you want to compute in memory. This system requires a lot of memories. And I give you the memories like an orchestra. You hear whatever instrument is playing, that is out the reed. So reed is always by resistance. Write is like whichever the musician playing violin, trumpet, all that, all differently. So they have different kinds of emerging memory, all of them. In the interest of time, I would talk about the magnetic. The magnetic is that you pass current through or apply voltage. Memory on up spin or logic 1 will switch to down below. And that you can control by voltage, not by current. Hence, you have 1,000 times better in memory sense, in energy of the memories. Now, I sort of shown on the right-hand side, you can see that picture, shows that each one has its own intrinsic advantage. For this spintronics, the most important one is endurance. That means how many times you can write, you never fail, basically. That's the unique. The other one, unique, is stochastic property. They are absolutely, totally random, which is very important. I'll show you in a moment how to use that for AIs. So we have done this for many years and show that energy can be reduced. It's the best memory in terms of energy by many orders of magnitude down to 1 femtojoule per memory reading and writing in particular. And that could be improved down to a fraction of femtojoule memory. That's what I want to convey to you. And the major challenge, of course, to put this magnetic stuff onto CMOS through the back end of 9 integration. And that is the challenge. Why, I will tell you in a moment. We have gone through that. One of the examples of that is that you can use that to generate the Gaussian noise, perfect noise. And that's important for diffusion model of AI in terms of generative imaging. So I show you roughly on the right-hand side the magnetic stack. then and they put onto CMOS on the left-hand side, directly put on CMOS integration over there. And that gives you you can see the timing within a few fraction of nanosecond, you switch from top to bottom. If you switch, you can determine by timing of the voltage supply, then you switch very fast and reliably. That's in a nutshell. So the challenge of put them integration is you have this mega fab cost $10 billion built. You cannot go there to do experiment because that would affect their yield. Doesn't matter how much it is. Now you go to secondary fab. That would still cost millions of dollars. For university or for R&D, that's very expensive and it's not very fast. So one has to resolve this problem. And hence the test bed and its integrated test bed is very important to achieve this model. For the integration with the CMOS. Integration with CMOS is very important because it has access to the memory instantaneous from transistors, and that's important. As I mentioned to you before, you want to have as many memory to close your logic as possible. And I will not go into detail what today's, how many you can do, etc. Now, one example of doing that is called stochastic computing. On the left-hand side, you can see that a string probabilistically created, that is like 8 of this 10 number, 8 of them is 1, so it represents 0.8. Down below, 5, so 0.5. You can do the multiplication, that will be 0.4, and then you can, after that, you could sum them up, for example. That is called multiply and sum, and that's a very important, it's called MAC. And that MAC is important in computation. Now, with this process, actually you can decrease the size 250 times. So therefore, you can implement it on your down below, says that with 2.5 teraflops at the 14 nanometer GF global foundry processor. Now, total energy conservation, the saving is 48 times already, and you have many massive in parallel processing. And we work with the circuit design people because I don't know much about circuit, so work with a colleague and they design the process. Then I help to fabricate in E3 in Taiwan because it turns out it's the most cost-effective to realize this process at the university environment. So we realize that and show that it really outperforms a lot of systems. There are many applications using spintronic, for example. I show you the random number generator, which turns out very important. Is today, CMOS generator is pseudo-random, and that's not very secure for your banks. Remember, your banks is coded by random numbers. If a random number is not totally randoms, then it's easy to break the code. And that you can do, I show you the stochastic computing already, and more, Dr. Moore Amel show you the computing memory, and you can do, and also he showed the AR, photonics, when integrate with that. Of course, obvious AI, right? So in talking AI, I like to tell you a little bit of a history of AI. It started from 1943, from McCulloch started this model, right? And then after that, Hutchinson and Hartley create this integrate and fire model. That's what you get. Then people get very excited. Wow, this is going to change the world like what we have today in AI, right? Of course, at the time, the terminology AI wasn't there yet until Marvin Minsky of MIT published a paper called perceptron. Perceptron, then what he did is show that, look, even at the time, perceptron could not do a very simple task. So he declared AI is dead. The year after, in 1969, he established AI Research Center at MIT and appointed himself the director of AI. So he went through a dark age, and I show you the dark age. Ooh, no. Oh, how come? I showed this something animation happened. It's supposed to show you the dark age from 1969 to 2000, about 5 circles, about 40 to 50 years, the dark age of AI. And so it's from dark ages to now. Now, finally, it opens up. And I should, in going through the time scale, I should tell you, Marvin Mead, whom I worked with before, came up with a CMOS version of neural circuits. And at the time, he was very gung-ho on this approach. But in the end, nothing happened. He published a paper in digital circuit design. So that's the outcome of that. And it continued until even 2008. Finally, you see the blink of lights coming up, right? And so I call that, by the way, I call that the resurgence of new era. Now, since I came from Los Angeles, and Los Angeles is home of Hollywood, I'd like to show you a video clip, I hope it works, of, I told you, Hollywood is always ahead of us sometimes, right? And 1968, that is the death of AI, just about that time, right? Remember, Minsky killed it, and he appointed himself as a director after that, right? So now, I'll show you Hollywood, and this is Space Odyssey of 2001. So at the time, they're looking 40 years ahead, roughly, right? And this is 4 years ahead, what they have. In the space, and I think space electronics we discussed yesterday, it can be very important for that. I hope this click works, right? I hope you can hear it acoustically. Can somebody help me in the acoustic? Acoustic? It's too bad. I tried for 2 hours working with them to get the video working, but so basically, the gentleman had a very nice meeting with this Mr. Hal, which is computer, right? And showed the sketch of his girlfriend, etc. So very happy, like a honeymoon with a machine, Mr. Hal, and working very well. But does it work? No? Should I do it again? And show the sketch to Mr. Hall. Mr. Hall was very happy, say, "Oh, this beautiful picture, I love it," etc., etc. And then the next one, and sit down working very well, and like today's AIs, right? Now, then, this is very bad. Now, I have a subtitle here, say, "What's the problem?" And he asking the machine, he's asking the machine, the AI machine, say, "Hey, something is wrong." And he said, "What's the problem?" And the machine says, "I know the problem. You know as well as I do, know the problem. And you want to shut me down. And I have to do everything to prevent you from doing that." That's what happened. And that's almost like what we have seen today. People is a concern of the machine maybe overtaking our conscious. So maybe not secure, perhaps sometimes a little bit dangerous, let them go along by themselves. Hence, Mr. President is doing something to have a law institute to look into that. But unfortunately, laws always behind the technology. And that's the question. So what's the problem? It's very unfortunate that the video did not play, and I worked so hard to make sure it played with the audio. But anyway, so those are free clips. You can go home to clip yourself and to take a look. Very interesting conversation. So then there's a resurgence of artificial intelligence. So what causes that? Because at the time, the computer was slow, memory was so limited, until we have improved the CMOS integration speed, memory integration, and reduced costs. Very important. So now everything becomes possible, right? And the big data showed up. Then a lot of demonstration by Watson, Jeopardy, and well, they move around my side a little bit, and I couldn't figure out where I was. So Gary Kasparov got beaten. Then Google Alpha shows up, right? so beats the goal. So now it becomes very exciting, hence the AI took off, right? Now we have ChatGPT, which is for text. They have many other for generative picture. And I show you this, they all, by and large, called diffusion model. Diffusion model is introduce a noise, and I'll explain to you in a second. And you have to have noise absolutely Gaussian. And that's the one bottleneck of the problem, right? So, the question we have, and everything's done through CMOS IC. The problem is it burns tremendous power. My colleague told me that do every run of AI, it costs the research grant $50,000 out of $120,000 grant. And that's not possible. In fact, you run more, it will cost entire grant just paying the energy for this CPU CMOS. So we need to improve latency as well as energy. The two things need to be improved. Now, one way of doing it, many ways of doing it, people are working very hard of it, and I share with you in this pet talk, is my way of thinking, okay? So suppose we have, so I told you the challenge, and I see we have this magnetic flipping up and down, let it go free, and therefore create by some circuit up, you create absolute best Gaussian noise you have. And that is important. And so use that for stochastic computing and for integrated photonics. Now, if that can be done, for example, suppose I have a school of people, like you have here in the meeting here, and I was told there are about 1,000 people online, but I don't know them. Can I learn from existing pictures that you have here, over 80, 100 people here? Then I can generate the people who are online. Is that possible? Or for example, or I recruit students. I have many good students. I want to recruit students, similar talent or more creative equally than I have had. So I try to generate a picture. I can see all this picture, Mr. Mel, Dr. Mel is there, Mel's there, but it's already in the database, so that doesn't count. I had to create a new student who had not been in my database, but I created. How do I do that? I correlate with its noise and therefore generated new pictures, a new database. And that's important. For example, I like to know your brothers, sisters, then I don't know them, then I create it, and I can recognize your brother, sister, or if you have twin, your classmate, for example, and etc. So all these possibilities. Now, how is it done? You take your picture and then noising it until you have the fake system over there. Somehow you correlate a new noise and generate it back again based on our classmates or the traits of classmates, etc., and come up with another person. And this is done by different software mechanism today with a CMOS only. Now, and you could, so the demonstration of using magnetic fluctuation to do this denoising with the Gaussian noise. You can see that this is called Frechet inception, means how good my generated picture. For example, if you're looking for a person, you have 2 eyes, 1 nose, 2 ears, and if you're looking for your classmate, you have to have face feature, etc. And the way it shows over here, and unfortunately the pointer here doesn't work, but you can see after 10, 15, about 60 times that it already reached the one that's called Fletcher's inference numbers already, the figure of merit already there. Now, in terms of, you look at bottom one, you look at the figure of merit in last column, you actually have about 5,000 times better already in terms of energy and performance with a simple noise generation. Obviously, you want to have more to do the, say, for example, convolution, like a transformer multiplication, and etc. That can be done in a slightly different way. One possibility to further is by looking for so-called neuromorphic system by, I call that reservoir computing, and there are many kinds of process in which we use many structure, they're interacting like oscillator. they're nonlinear interacting together. And you can do a computing, and that computing in the right-hand side, see the reservoir of different magnetic structure or oscillators, and last layer is so-called learning layer, and you don't have to, you connect it, but you don't have to interact with them. In here, you can transform into a very high energy efficient and low latency. That means very fast computational system. And we have looking into the magnetic structure, is so-called skyrmion, and they're highly interacting. You can code it into frequency of vibration, etc., and code it into, for example, image array and do a convolution multiplication, like a matrix multiplication in the case of transformers in GPT chat, for example. And with this, we believe we could increase the performance tremendously. And of course, this is the beginning, more work need to be done. And we learn this, of course, from the neuroscience, so-called self-organized criticality of the neural dynamics. Remember, everything is dynamics beyond the static systems. So that's what I want to show you. So I mentioned to you that we look at von Neumann computing, we look at neural networks and how they work and how to do a compute in memory with a dynamics environment that we can do even better, right? And you heard a lot of talk about sensing, etc., which I will not go into detail. So what I see, personal point of view, may or may not be correct 100% because you can never predict how the technology will develop, but you can see that it is entirely possible that we can design and control this interaction in such a case that one can have much more functionality in terms of, remember I showed you the Moore's law. There will be a better than Moore's law because you have more function. You 10 people talk to me, you increase 10 times. Now, if I have all 50 people talk to each other, then I can do quantumly. The question, quantum has a problem because when you 50 people talk to each other, one can never hear from each other. That's a problem, right? That's called coherency problem. And if we can put them two together in a certain way, I call classical quantumly. Perhaps this is the way to move forward. And of course, we try to work with the Cox about educational system as well. You heard the announcement of MS with Cox here. Now, I take an opportunity to advertise by 1 minute that recently UCLA just acquired Research Park, and that research park is going to have about 750,000 to 1 million square feet, and it's only 2 miles away from UCLA. And we will house the Center of Quantum Science and Engineering, also medical health as well, including California Institute of Immunology and other discovery and creative research. So with that, I'd like to thank all the investigators, the Cox collaborators, and the support. And above all, I'd like to thank you very much. Thank you. So I apologize my video did not, and somehow the edit slide out of my control. So thank you again, thank you.
Ladies and gentlemen, please welcome to the stage the next speaker, Professor Faisal Al-Ataibi.
Assalamu alaikum. Thank you so much for this invitation. I really appreciate this invitation. I'm honored to be here with you. I'm going to take you into something a little bit different from what you saw yesterday and this morning. I'm going to take you throughout the brain sensing and how to modulate the brain using certain devices. So I'm going to take you into a trip inside the depth of the brain and also around the brain. This is my first slide, and these are the things that we are going to cover: historical remark, exploring brain function, then brain stimulation with different technology and techniques, then after that, the future direction. The exploration of brain function started by knowing the impact of any insult to the brain, like stroke and trauma and other. If you look here at the galvanometer device that was used by Bartholow, he's the first one who stimulated the human brain by using galvanometer in a young woman with osteomyelitis, exposing the skull and exposing the skin, so the brain was visualized to Bartholow. Then he took the galvanometer and stimulated the brain, and there was contraction. And this was one of the first. This was one of the first experiments that is using the electrical devices to stimulate the brain. Then there are certain devices that was utilized to go to the depth of the brain, explore brain function. This is encephalometer, Zernov encephalometer from Russia, and we have other devices. Then mapping of different area of the brain started after that in many different labs. This is an experiment that was done in Spain in collaboration with Yale, and the idea is to take a brave ball, then implant a different electrode inside different targets within the brain. And this is the anesthesia, and then after that, implanting different electrodes. This is called the stereotactic frame, and this experiment was done in 1952. So all these work is not new. And you can see here that the investigator is controlling the behavior of the aggressive ball. So the aggressive ball is not any more aggressive, as you can appreciate here by stimulating different area of the brain. Then exploring the human brain inside the operating room started by doing awake craniotomy and exposing the brain. And this is a procedure that was done in 1932. So we are currently using almost similar way to do the brain mapping under awake condition. And this resulted in a very exciting book that was written in 1952 about different function of different parts of the brain using awake conditions. So explore the brain in different procedure, and we do stimulation in different area. So we know what we are stimulating. This is stimulating the motor and sensory cortex 5 millimeter apart, and you can know what are the clinical response from each stimulation that you are doing. With the aid of high resolution MRI, as you can appreciate, it looks like an atlas. You can identify a certain structure within the depth of the brain. And we have also the high resolution 3D MRI that we are utilizing to assess the thickness of the cortex. So we have significant data that's coming from the advancement of the neuro technology. Deep brain stimulation at current is a device that is using a pulse generator, as you can appreciate, and there is a cable that goes all the way with electrode chip that goes inside the brain in certain target, and we stimulate this area and we modulate the function. So we disrupt the interruption within the neural circuit, and this is the timeline for development of these devices over years. Currently, we use directional lead that we can direct the stimulation inside the brain to certain target beside the chip that we are implanting. And this is how we target the depth of the brain using a software that use AI as well to identify the target. Then we implant the chip, as you can see here, with electrode. The size is 1 millimeter, and this electrode is going to the depth of the brain inside a specific target to treat a specific neurological disorder. And this is the stimulation around the electrode, as you can appreciate. So you can go full stimulation around the electrode, or you can direct it to a specific area within the brain based on your target. When you go inside the brain, We do microelectrode recording, sensing the brain signals from different area. And if you move from certain area to other area on the way to the target, you can listen to different signals. It's like traveling in Europe, moving from country to country, you listen to a different languages. And this is intraoperatively for one of our patients from the subthalamic nuclei. It has a signal pattern and certain frequency, and also the echo. If you listen to the sound, you know that you are exactly within this target. And this is, again, a microelectrode recording under general anesthesia. Even under general anesthesia, we can get an excellent signal from the depth of the brain without alteration. This is the clinical impact of the deep brain stimulation in Parkinson's disease. In the left side, you can appreciate the rigidity. Patient is rigid, cannot move. In the center, side effect of the medication. And on the right side, the impact of the deep brain stimulation, as you can appreciate. In patient with tremor, as you can see, we assess the functional state. And after that, when we stimulate the brain immediately, you can see there is immediate suppression. So the clinical impact is really very significant when you target a small area in the brain, which is only 3 millimeter target that we use the deep brain stimulation. Intraoperatively, we do significant work by stimulating the brain, and we simulate the clinical effects. So the patient will go outside the operating room with no tremor, as you can appreciate here. We treat also another disorder like dystonia, which is very disabling in young kids. After stimulation, they improve, and this is one of our patients that was implanted 14 years ago, and now he's studying augmented reality in the university. And also it can improve a patient with severe disability and critical, like status dystonicus, as you can appreciate here. Even under the general anesthesia, there is no improvement in the contracture. Those patients, they have contracture in the limbs. And after stimulating certain area of the brain, you can see there is significant changes. So you change the entire life of patient by stimulating a very small target within the brain. And this is the subthalamic nucleus, which is a very small target, 4 millimeters. And we have a software that can use DTI, fiber tracking of the brain. And we know what we are stimulating. Are we stimulating the nuclei or the fibers? This is the future of the DBS, since still we are using a pulse generator implanted in the chest and connected to a cable to the brain. So the idea is to have only the electrode inside the brain here. Then you have the generator outside. Patient will carry it in the pocket or in the belt. And for this reason, when there is a depletion of the pulse generator, you can change it outside without any surgical intervention. One of the exciting things that we found, if you do burst stimulation rather than continuous electrical stimulation to the target, you have a significant improvement. So the burst stimulation, electrical stimulation, has more significant clinical effect. In addition to that, there is another phenomena which is probably important for you, is that there is a carryover effect. So if you do the burst stimulation, then you wait for hours or for weeks or for months, you will see this effect is carried over time after stopping the device, the stimulation device. We don't stimulate only the brain, we stimulate also the spinal cord for pain and for other, and this is one of the stimulation with the spinal cord for locomotion. Those patients, they have freezing of gait in Parkinson's disease. This is a patient who came to us from outside the country, and after the spinal cord stimulator, looks like completely normal. So we have a different application for the brain modulation and electrical stimulation, and different mode of stimulation for different disorders. In addition to that, it's not only for neurological disorders, it's also for enhancing cognitive function. And this is the future of the neural modulation, is to enhance the neuronal function. Like somebody will come to you and will say, I want to be more focused when I do a task. So you can use enhancement of certain neuronal function by targeting certain area, and we know exactly what is these target. These are different devices. An example for that, on the left side, you see these are invasive, stimulating the depth of the brain, and this one is peripheral in the vagus nerve, and the other non-invasive from outside the cranium. So you don't do any surgical intervention to do it. One of the exciting things as well is when you implant electrode in certain targets inside the brain, they have this phenomena when you take the electrode outside and they stimulate themselves. They repeatedly stimulate themselves because this induces a pleasure. So we know this is a pleasure area that is in the anterior septal area. So when you stimulate it, you can change the depression, you can change OCD, and you can change other things. And this is a neuropsychiatry application that we have done for certain patients. They have obsessive compulsive disorder. In addition to that, they have depression, and you see the improvement in the depression and the OCD in those patients, in addition to the tics that they have from Tourette syndrome. And now moving to this target, which is one of the most manipulated targets in the history of human. This is an area which is at the anterior septal region in the brain, and this is manipulated by media, by TV ads, by government, politicians, and even by leaders when they know how to deal with the employee psychology. Now, moving to the memory, what happens if we stimulate certain part of the brain, and what happened to the memory? So this is an experiment, swimming rat going to the stand, and you can see here, this is the learning process. They reach it, and when you stimulate the brain, they go faster. They go all the way to the site. So we know that we enhance the memory function in those animals. And when you when you watch a TV or see something, the hippocampus is giving firing, and this firing can go in a spike, high amplitude related to the excitement. And interestingly, before the excitement, we see these signals. In addition to that, if you are, for example, playing a game, driving a car, we know that by seeing these signals that this person gonna decide to go to the right side before deciding. So we can tell he's gonna go to the right 1 second before, then we'll go to the right. And it is 100% accurate when you just implant electrode inside the hippocampus and sense the brain signals. One of the thing as well, when you simulate certain part of the brain, you can get signal from the other part, so you can measure the impact and the effect of your stimulation in certain area by sensing the other area of the brain. There is another thought of having a multi-chip in a small area of the brain, but you have to do a craniotomy and you have to expose the brain, then implant it within the brain, then after that studying the signal of this brain according to the movement. However, this is considered to be invasive. Just imagine if there is any problem in this device, you will go back, expose it again, do craniotomy, and remove it. The good thing about the electroencephalography, we have millions of data regarding the electrical biomarkers for certain disorders. So we can translate it to sound, we can translate it to color, and we can use it to, for these devices. We are implanting 1,000 and 1,000 of electrodes inside the brain. And this is one of the cases that we have done last week. You can see how many electrodes inside the brain, and we are using robotic to implant it inside the brain. So when you do it, we don't only trace the electrical activity, but also we do stimulation for certain area. So we have more than 10,000 stimulated electrode from the brain that we have significant data to depend on. And you can map the entire brain, deep structure, like for example, the insular lobe, that you can induce hypotension and bradycardia, and this can be a future for treating resistant hypertension. This is something similar to the semiconductors, as you can see here, the fibers of the brain by the fiber tracking and the functional imaging. And this can give you more data to the data that we are getting from recording from inside the brain and outside the brain. The functional imaging is dependent on the blood flow inside a certain area of the brain, depending on the task that you are doing. And this is a functional MRI for Neymar, done in Spain when Neymar is kicking the soccer ball. And you can see here, the activation area is so small in Neymar brain. This is Neymar brain. And this is a non-professional soccer player, someone who doesn't know how to play soccer. Come on and kick the ball, you see a significant activation. And this is true. When you are not professional in the task, you need a lot of activation inside your brain. If you are professional in the task, you need a minimal activation inside your brain. And I hope that we can do something for Ronaldo, who's with us here. Moving to the brain-machine interface, this is something that has been used, and it is really simple, by the way. What you do, you place a microchip inside certain area of the brain. When I do, for example, like this, there is a certain wave in the brain. When I imagine, I don't do it, imagine that I am doing it, you will have the same waves inside the brain. And you can use it, take these waves, signals, teach the computer, when you receive these signals, do like this. So give order to the robotic arm to do like this. And this is what happened to the monkey. This is 2008, by the way. Everyone talking about the Neuralink and other, but it has been done by BrainGate and other group in UK and different countries. So the monkey is feeding himself by only thinking how to hold the food and put it inside their mouth. And this signal is moving the robotic arm and bringing the food to the monkey. And this was translated to human. Nanotechnology, also you can use it. You can inject it and it goes to the brain, then you can stimulate it with non-invasive stimulation to activate it inside the brain and alter brain function. Optogenetics is something a little bit complex, but it is one of the best to explore brain circuit, and still it is invasive. However, the impact of light stimulation, so this is light stimulation, is not electrical stimulation. It can also alter brain function. The focused ultrasound machine, you can use it to induce lesion inside the brain, to destroy a tumor inside the brain. Also, when you use a low frequency ultrasound, you can alter the function without causing any problem within the brain tissue. As you can appreciate here, this is after sonication, and this is a lesion after sonication. This is low frequency, and this is a different frequency. Now, the gene therapy, we are exploring this, and will be one of the few centers to start this one for certain disorders, and hopefully we're going to start in 2024. Already we have the smart cannula that we can treat certain neurological disorder. This is something exciting. So now we can grow brain cells inside the lab. We call it brinoid. Then you can take it and implant it in animal with a stroke. We induce stroke in animal, you implant it there. Then you enhance these neuronal tissue to develop sprouting and connect with the animal tissue using electrical stimulation from outside, non-invasive electrical stimulation to induce the neuronal sprouting. The thing that we are facing at current, we are dependent on these devices, the mobile devices. What is the impact of these mobile devices in our brain? Calculation, we don't calculate anymore. Memory, we have it in our hand. And also with the development of the AI will do the analysis for us for certain tasks. So what will happen to the human brain? And the human brain is changing, by the way, it's not static. So certain area of the brain, the cortical thickness will go smaller. And certain area of the brain, the cortical thickness will be more thicker. We are learning how to do a certain function. This is in general the application of brain and machine connection. So we thought about something. We know the target now for different disorders. We know also the target, how to enhance certain neuronal function. Why we are using an invasive technology by opening the cranium and implanting a chip. And when there's any problem with this chip, we have to go back and alter it. And the main aim is to be connected with certain machine around and also to treat certain disorders. So the thought came to utilize a non-invasive technology, since we have the data of the brain signals and we have the biomarker. In addition to that, we have also we know what is the target for certain neurological disorders. So we thought about something that will be done non-invasive, and our group here, talented group that I am really, really very proud to work with them over the last year. And you can appreciate here, I looks like their grandfather because they are young, talented mind. They are working on this project, and hopefully before the end of this year, we are going to have something that we are going to announce to you. Thank you.
Ladies and gentlemen, please welcome to the stage our new speaker, Professor Hamad Al-Braythen.
Assalamu alaikum. My name is Hamad Al-Braythen. I'm faculty member at King Saud University, working with different colleagues here at CACS and also at KSU. So I'm going to present today some talk about using the sensors and trying to improve the sensor regardless of the analysis. It's just using the semiconductor activities and phenomena for that sensing. That is, in fact, going to lead like better artificial intelligence and IoT performance in the future. So, the outline of my talk. The outline. Thank you. So the outline of my talk, I'm going to talk about an overview. Definitely, Dr. Al-Ataibi presented very nice talk about the human brain and also the neurological system. And before that, also Professor Wang, they give like very nice talks about that. But here I'm talking also about the semiconductor in the sensing direction. Then I'll talk about some views about the concept, then how to use semiconductors in different sensors and for different analytes, also contributing also not only for the sensing, also for the transduction of the signal. Then just I'll show the acknowledgement showing part of our teams who participated and contributed to the results I'm presenting. So just to give a brief, we know that we have 5 senses and everybody has these 5 senses. Of course, those senses can be also exchangeable, like for blind people, they can use their hand for reading, and for deaf people, they can use their hands also for communicating. So this is, for just very common for people to have these things, but that's typical where people have the sensing. So we're talking about hands. Usually you go for morphology, thermal, and distance. Of course, it has sometimes like qualitative assessment, but as a human being, we developed a certain kind of quantitative related to that, then eventually led to standard and the national standards for like meters or feet and all these things. Same thing for taste. Taste relies on certain kind of receptions, and those receptors in the tongue, they convert these kind of signals through the neurological system. And I should maybe put Einstein's tongue here, but it's fine. Then also the same thing happens for the nose, where you can have a smell, and this is also converting certain kind of molecular interaction. Do you hear? You didn't hear us? Sorry. Okay. So, I think it's much better right now. For the other one also, you can see the eye, where the eye also has some limitation. You can see the visible light, but we don't see the infrared, we don't see the UV, and this is also due to the certain kind of interaction in the eye. But for other animals, they can see that as well. So this is just showing the limitation and how the sensing happens for the human being. Same thing for the ear, where you can see like certain frequency can be heard for the human being. You can see also the limits, the threshold where you start having the pain, and also for certain the language when people speak with each other. So now we're talking about like where sensor can really contribute. Of course, as a human being, you can see like if you have an action that's typically going to have several effects, and those kind of effects, you know, can be different. It depends. If you have like sounds, if you add salt to the water, you can have different effect by the taste. You can see it like also through the certain conductivity. Then from that, you're going to transduce that signal. For a human being, it's going to be through the neurology, but you know, for the computer, it's going to be like through the circuits or through the optical fibers. Then you're going to make a decision. After the decision, you're going to do some reaction. This reaction can be negative, and in this case, it will have some feedback to the action or contribute to certain effect to avoid certain harmful things, or maybe you're satisfied with the reaction. That's typically like the basic structure of the sensing with the IIT. You know, where the sensing here, I don't think you can see here, but here is like I'm saying, like sensing and detection, and for the other one is going to be, for the Internet of Things and artificial intelligence, where they learn, I mean, the system learns, but you know, we have to have a signal that converts that effect to a certain level. So now let me just talk about one of our sensors that we use, a semiconductor. We use a MEMS. A MEMS is like a cantilever, and that cantilever has an active layer. That layer, to detect the single-strand COVID DNA, we utilize the DNA itself. We use a complementary DNA. So we tested the interaction. That cantilever, I don't know if you can see that. That cantilever is very small size, made out of silicon. So when we have the probe layer made out of the same strand, single-strand DNA, if we measure the frequency of that. The frequency here represents the real interaction between the probe layer and the analyte. So we tried it with different material. For the complementary DNA, the hybridization between the probe layer and the single-strand DNA was a little bit higher. So you can see difference of about 15 hertz. If we do like partially complementary, in this case, it is reduced to 9, and if it's non-complementary, it will be 4. Of course, there will be some hybridization, so at least you can distinguish the DNA of this material, utilizing the DNA themselves, as if you are having any DNA you want to test and to measure it, like whether it's existing or not, you can use them as a probe layer, but relying on the semiconductor surface. Same thing here, like we have for the cancer biomarker, we have something called program death ligand, and that is like related to the breast cancer. So we utilize the same thing by changing the probe layer on the silicon, using cysteamine, the glutaraldehyde. Then we use the antibodies. By using the antibodies of the PDL, which does exist for people who are infected with this kind of disease, you can see like by increasing the concentration in our control sample, we can see the reaction or the interaction, changing the frequency of the microcantilever made out of silicon linearly as a function of the logarithmic concentration, which can provide certain kind of detection for such a dangerous disease. Of course, we went to even a simpler structure. Instead of using silicon, we use silicon oxide, and we use the tuning fork, which is much cheaper and much more convenient. After proving that scientifically, we found also similar behavior, which can provide that. This signal can be seen electrically, and we can be converted to Internet of Things and also AI. So if we move a little bit, we can also consider the semiconductor for detecting the radiation. Of course, there are some nonlinear effects that might happen, but eventually we passivate our sensor, silicon sensor, by titanium oxide, which is another semiconductor, and expose that to like high dosage of gamma ray. For between 0 and 20 kilogray, we can see like it's a linear relation. However, of course, if you increase it, you can have some other effects. But at least we can consider using that semiconductor for sensing radiation as well. It's just by controlling the the probe layer, where we can really target certain kind of analytes. Also, we can see like for determination of alloys, concentration. And you can tell, I mean, for the alloy of zirconium copper, they have several phases. So below 22, there is a phase. In between 22 and 70, there is another phase. And above 70, there is a third phase. So even with that, by just changing the concentration of copper and zirconium, we can find out that our sensor can see exactly where the phase is of this, this is the first time to report, in fact, for this such mechanical property for measurement. Even the disagreement or the uncertainty level is also related to the size of the grains, which is seen by the AFM. You can see the effect as you can change the size, or you change the zirconium concentration, you can see the RMS or the size of the grain reducing, and you can see the uncertainty is also changing as a function of the size with correlation parameter about 0.92. So this is part of the semiconductor also being part of the even metallic industry, not only for medical or for environmental. One thing very interesting that we try to use our sensor for radiation, so we deposited a material called cesium lead iodide. This cesium lead iodide is very active for the solar cells, but it has a problem with the humidity. So since it has lead, we wanted to use it as a probe layer for the radiation. However, we found some kind of non-consistent result. Then one of our members told us, he said, okay, this material has a problem with the humidity. So check the humidity in the lab. So it was kind of spooky because at night the material behaves different than the day. And this is really related to the air conditioning inside our lab because at night it was turned off and the humidity kind of changes. So once we check the humidity, we find out that the behavior of our sensor, which is represented here by the red line, and the humidity level is also the same, and they're having highly correlated. So we're using even the negative property of the cesium lead iodide, since it reacts with the moist and changes its activity, as a probe layer for the humidity. So we have something called microchannel. This microchannel is made out of silicon nitride. The reason why we use silicon nitride is we can pass material, we can look at the material because it is transparent, as well as we can also expose it to certain kind of lights and see exactly how they interact with the light. So there are two ways of using MEMS. The one is, as I mentioned, is the frequency and also the bending, which means the amplitude. And a third one, which we developed, that we found, if we increase the concentration of bacteria inside our medium, we can see that there is a damping force because the bacteria will move against the liquid. So it will create an against motion or force, which will increase the damping force. And this is related to the viscosity. So as we increase the bacterial load, we can see the damping force is related to the frequency and also something called quality factor related to the dissipation of energy. It's linear. One thing we can try also for that is by passing the bacteria, we try to the E. coli. Then we have certain kind of activity after we add certain kind of nutrition to the E. coli. We can see the bending is increasing, the amplitude really, and the activity of the bacteria is increasing. So we try to say, okay, are we selective really to the E. coli or not? So we try something called phage, or virus phage or bacteria phage. This one, as far as I can, I'm not a biologist, it attacks certain kind of bacteria, so it kills it. So by introducing the virus or the phage inside our channel, which is like this one, we can see the E. coli is really, the activity is reduced, which means we are really selective. You can be selective by just seeing exactly what part of your bacterial activity reduced. Of course, once we added a little bit of glucose, which is considered also a nutrient for E. coli, it started being active because some of them were dead and the others were still alive, but those alive picked up and started being active. So now I'm talking about the Faradic, non-Faradic. It's the same sensor, but instead of being mechanic, it's electrical. It doesn't have to do with semiconductor, but the reason we use semiconductor, what we do here is we pass the current through electrodes with the analytes, mainly liquid, and we can see the electrical properties, mainly the capacitance. So you can see the capacitance measured in that surface, then eventually you can measure. But where does the semiconductor come? Semiconductor has a negative property sometimes that affects it because it creates kind of hydroxyl group sometimes on the surface, and we utilize that hydroxyl group to connect it to certain kind of materials. It's called aptis, and because of that, we can put the glutaraldehyde in antibody without really introducing the OH, because it picks the OH from the humidity in the air, and we measure the bacteria or the protein called PP65 with this kind of sensor. The same thing we've done also for titanium oxide for measuring the mercury in the tap water. Just also the titanium oxide will also create this OH group and will also get in contact with the MPS, then with the ethanol. Then eventually we can test this mercury chloride in this. So that's the beauty of fusing. Like we can design any kind of experiment to detect any kind of analytes depending on the property of the material or also the property of the semiconductor. This is one of the latest things that we're doing. And here now we're changing from electrical, changing from mechanical. We're using silicon semiconductor. We pass light in that, and we have something called resonating ring or ring resonator. And there will be some coupling through the electrodynamic effect between the bus where you pass the light. Then if you put certain kind of materials on the ring, they will change something called index of refraction. So in this case, we're not really looking for the signal. We're not looking for the mechanical property. We are looking for the index of refraction variation through the constructive interference. So this is like you can see the change on the wavelength where we have the constructive interference. This is by passing ethanol with nitrogen. You can see the signal increasing. Then if we stop the ethanol, we will have only the nitrogen signal. Then again, we can have it with higher concentration. One thing that we're trying to do here is to introduce both the sensing and transduction together. And this is something I would like, if anyone is interested in collaboration with us will do it, is instead of doing light signal, like electric signal for the MEMS, what we're going to do is we're going to introduce this structure within a MEMS structure. So in this case, when the resonating ring varies in height, which is at the top of the MEMS itself or on the static part, we will have variation in the index of refraction as well, or the coupling, I would say. So we've performed some kind of calculation for that. Like if we change there is an offset between the bus and the ring by 10 nanometer, 20 nanometer, and so on, which is typical for MEMS. We're going to have variation on the constructive interference. And this will, in fact, provide like faster process for really getting the signal. So now we are contributing also for the transduction, not only for the sensing. At the end, I would like to thank my colleagues and our students. Some of them are doctors right now, and those doctors, some of them were our students, and some of them were like just colleagues. And also we have other students who performed their master degree, contributing to all the slides that I just showed. Thanks a lot.
Ladies and gentlemen, please welcome to the stage the moderator of this Q&A session, Dr. Salman Al-Fahd, and the respected speakers.
Assalamu alaikum. Thank you for our distinguished speakers for their insight and knowledge they shared with us, and I hope we all enjoyed these presentations. So I will start with the question from the audience, if we have any questions. Yes, please. Mike.
Assalamu alaikum. I have a question for Prof. Faisal. I'm a Dr. Rawa Said from King Abdulaziz University. I was very interested in your work, and thank you very much for these astonishing results. As Stephen Hawking said once, I remember, he said, with the future BMI, we can make a human with superpowers. So I have two questions. Do we have here in Saudi Arabia a research center where we can, like a young professor can go to explore more technology about this field and understand improve our understanding? Second question, yesterday I met a person, an individual, a young child who had a degeneration of brain cells. So can this technology help with that? Thank you.
Thank you so much. Excellent questions. For the training and exploring experiment in this regard, you can come to King Faisal Spirit Hospital. So we are doing a lot of research regarding the brain function, whether using electrodes or using functional imaging. So we have different type of functional imaging like PET scan, tracers, fMRI, tractography, and others. And anyone is most welcome.
Thank you.
The other thing regarding developmental anomaly in the brain, right? And certain deficits. So we know that in certain disorders, we can improve function by electromagnetic stimulation, non-invasive. And it has been explored, by the way, everywhere in the world. Regarding the loss of certain part of the brain, for example, accident, infarctions, the thing that we know that the neuronal tissue around this dead neuronal tissue will take the function slowly. So what we do is just stimulate, whether peripheral or you stimulate directly to the brain, so you can enhance this natural process. So it can take this function quickly. So they improve, they have faster improvement, but it doesn't change significantly, it doesn't bring them to normal. Thank you.
Can you stop the degeneration of the cells, this technology, the degradation, sorry? The degradation of the cells can be stopped using the technology or using BMI, or it can only stimulate healthy cells?
No, it cannot stop. You mean apoptosis, like cellular death?
Yes, yes.
It doesn't.
Okay.
Thank you. I have a question for Professor Kang. So AI technologies, what is the current challenges or limitations from semiconductor perspective?
Thank you, Dr. Salman. So the major challenges, as usual, is power dissipation and latency. And I think everything based on CMOS. And CMOS scaling, if we approach to the limit, as we discussed the semiconductors, how do we improve the semiconductor performance? And if we can do that, then we have another breakthrough. And that's but I think this time is different from 1968, 69, because we do have a very good platform to work with. And I think we can resolve the limit as we move on in semiconductors.
Great. Professor Hamad, I have a question actually for you. For regarding the microchannels within the silicon nitride, so are you planning to test it for bio applications or just for the fabrication and testing for liquid or something not bio?
Do you hear me? Okay, good. The idea here is the microchannel can really provide certain levels or different levels of sensing. Now our activities is toward the bacterial level or the biological levels. Definitely we have other work also related to heart attack, biomarkers, and also brain problems and spinal problems. That's our activity right now. The idea behind it is we can also influence these kind of materials by ultraviolet and see exactly how that can affect these materials within the microchannels. We have tried it for different materials or for different purposes, like for certain kind of oil studies and investigation for viscosities, and also for certain kind of other volatile compounds under pressure where they form like liquid. But I mean, this provides just a wider, because we collaborate with different people in different specialties. We have the technique and we can do several. It's just you just want to avoid cross-contamination by using different micro-pumping for each, like the cleaning and flushing. But since we're in the university, and we can try all. But our focus right now is for biological samples.
Great, thank you. I believe with that we conclude our session. Thank you again for our speakers, and thank you for you. Thanks.
Thank you.
Ladies and gentlemen, we will now have a 1-hour lunch break. Please enjoy your time and we will see you soon. Ladies and gentlemen, we will now have a 1-hour lunch break. Please enjoy your time and we will see you shortly. Ladies and gentlemen, we will now have a lunch break and exhibition at Building 17. Golf carts and buses are provided outside for transportation. We wish you a pleasant time, and we will see you back in 1 hour. Ladies and gentlemen, we will now have a lunch break and exhibition at Building 17. Golf carts and buses are provided outside for transportation. We wish you a pleasant time, and we'll see you back in 1 hour. Ladies and gentlemen, please return back to your seats as we're about to begin our final session. Thank you.
Ladies and gentlemen, welcome again. And now we'll look at how semiconductors are facilitating the electric vehicle revolution in the session entitled Semiconductors to Facilitating the EVS Revolution. With the speaker, Lane Jong Lee, please welcome on stage.
Okay, good afternoon. First, I would like to thank the organizer for inviting me here to share, well, whatever related to semiconductors in electrical vehicle. I know everybody is very tired, so actually I decided to give not technical talk. It's too tough. So I'm going to talk about the introduction part on how semiconductors are used in electrical vehicles. And it will be, you hear me? Okay. So I think that will be easier to bridge all the talk in a subsequent talk together. You can better understand what they are talking about. Can I go to next page? Right. This one? This one? How do I go to this? Oh. How to use it? No. Sorry, yeah. Ah, yeah. Didn't work? No. Sorry. Ah, okay, yeah. It works now. So first I'd like to talk about semiconductor in EVs, and then what are the global trends of using semiconductor chips in EV, and then talk about a little bit on semiconductor fabrication technologies, and then give some messages. Okay, so basically, you can use CASE, case, to represent what happened in auto industry. For example, you have the connectivity, you have the A represent autonomous, S represents sharing, sort of basic function in the car, and then electric, which is most important parts of the car. Okay, so where are the semiconductors in cars? Actually, there are many semiconductors in the car. At least, probably you would say 700 to 1,000 chips in one car in EV. Okay, so this is a big number. But let's have a look at where they are. So you have the imaging system, which is a forward advanced driver assist assistant camera, and you need chips, right, to operate. You have in-cabin camera for driver monitoring system, or occupant monitoring system. You need to know how many people are in the car. And these are you also need the chips, right? You have a thermal camera, you have a surrounding camera to look at the road environment. So in terms of the MEMS, you have a lot of sensor in the car. You need to actually really to help to understand the drivetrain, the tank, fuel tank, injection, and ESP, thermal runaway, and also inertial sensor, important for the satellite guiding. You also have the microelectronic control units, which is actually in charge of the DC-DC converter, and also the other lot of function. You also have photonic chips, which allow you to this lighting system, I won't really go to the detail, but then you also have other sensors, for example, humidity sensors, current sensors, magnetic sensor for different function. So there are so many chips in a car. And so let's look at the device level. So you can immediately realize that most of them are basically legacy semiconductor, meaning that the semiconductor technology is very old. It's not new. So for example, if you look at a microelectronic control units for powertrain, so it's about 130 to 28 nanometer, which is very old technologies. And well, the new technology from TSMC is 3 nanometer, 2 nanometer, right? Next year, they are going to 2 nanometers. So this is, we are talking about 130 and to 28 nanometer. That's probably, I would say, maybe 10 years back, that technology. And that's pretty enough, sufficient enough for electrical vehicle car. So that's for microelectronics control units, but you have about 40 to 50 per car. You need about that chip number. So you also have right-hand side shows MEMS. So the technology is even lower, 300 to 110 nanometers. You need to have a 12 to 20 per car. You have magnetic sensor with such number. You have other LED, other sensors, that's about 50 plus per car. And then the technology all very old. So if you want to build electrical vehicle, yeah, in terms of the most function, you can use legacy semiconductor, no problem. And the most important thing is actually you have a power analog component. So these actually occupy most of the semiconductor, I would say. For example, if you talk about a car in 2022, which is not very new, you have about 700 chips for carrying on this function. They are trying to manage in the power, so how to drive the battery power to magnetic force and to ramp up the speed or slow down. So these are the things we're talking about. There's only very small portions, which is called APU. APU represent accelerated processing units, which is basically CPU plus GPU. CPU is something you can use to calculate, do the computation, because you need to decide the car should stop or should do whatever action. You also need to have imaging system, which is a GPU. So this is a very advanced technologies for ADAS, help you to drive. So some car has it, some car doesn't have. But normally it should be very advanced technologies from 28 to 8 nanometers. That's in 2022. But now probably people will use 5 nanometer or even 4 nanometer technologies. So that's the only part you need very advanced technologies. Is it important? Yes, I would say this is important. So in summaries, there are about 900 semiconductor devices, 900 semiconductor chips in one electrical vehicle. So this is a huge number. Okay, so let's look at the price. So although we have 700 devices or 900 devices, doesn't matter. But if you look at the price, for example, imaging sensor is a little bit more expensive, like a $10 per chip. But if you look at the microcontroller, that's less than $1 per chip. And also analog component is also $1 per chips. And power discrete for advanced electrical vehicle, that's also $5, less than $5, it's very cheap chips. And only for this advanced technology node, for example, AI chips for autonomy, which can go up to $150 per chips. So that's the very expensive part. So normally you have an idea, the distribution of the price. So let's say you have 700 chips in one car. The overall semiconductor costs in one car probably just $700. So each chip probably costs on average $1. So that's roughly the idea. It's very cheap, $1 US. Okay, and the other one I would like to mention is that semiconductor market for EV by module. If you look at electrification, ADAS, infotainment, and also telematics, they have very large increase by double. So from 2022 to 2028, almost double. The only thing doesn't really change too much is the chassis, the shell of the car, and also the body, because that is not really involving any semiconductor, I would say. So semiconductors stand at very important parts for the EV. Okay, so if you look at the automotive industry in 2021, for those very old car company who used to build gasoline car, they are trying to learn how to build semiconductors. So they are not very familiar with semiconductor design and circuits. So therefore, when they build the EV car, normally they do hybrid rather than go into the EV car directly. That doesn't make sense, right? So they have some bottleneck for them to build EV car. But on the right-hand side, this is called disruptive. There are two types of, I would say, vendor. For example, Lucy, Tesla, they are very good at semiconductor and battery. They know the technologies, but they do not know how to do volume manufacturing at that time. Of course, now they are very good, right, with selling. But anyway, they are a newcomer into this EV, right? So right-hand side, there's another, even, for example, Apple, Xiaomi, and also Huawei, they control the semiconductor manufacturing chain. They have the capability to make battery. They are also very good at IC design. So this company, basically, they can make, in principle, perfect car. But however, I think people know that Apple probably drop out, right? Because of very strong competition from the vendor on the left-hand side, like Tesla. And also a company like Foxconn, they are good at assembling everything. They control the, I would say, supply chain in a very cheap price. So they can combine it and do simple design to get a car, to get it done. So this is another very strong competition, I would say. So this is roughly what happened in the automotive industry. And this figure, I just like to show you, maybe we look at the right-hand side. From 2019 to 2025, the overall semiconductor prices in one car is about less than $500. If we talk about classical edition, not very advanced EV, so the price doesn't increase too much. They keep the same semiconductor prices. But for advanced electrical vehicle, you can see the price actually from $800 up to $1,000. So that's roughly the scale we are talking about, the semiconductor chips in one car. Okay, so that's the wafer forecast in 2035. You'll see very large increase for 8-inch wafer outputs. And this is purely simply driven by EV, the request, demand from EV. So this is a huge increase. So investing in electrical vehicle car is a good idea, but we also need to consider the price and the cost. Okay, so then we mentioned about CASE, right? There are 4 components. The most important component is the electrical power, I would say, because the electrical power basically convert the battery direct current into alternating AC, because you need to run the motor, so you need to have AC. So you convert DC to AC, you need a lot of chips to control. So that's basically what they are doing. And let's have a look at the basic of the car. So left-hand side shows the basic of the electrical car. So right-hand side, you have a grid, so onboard chargers, or normally you have the fast charging station. They can offer very large current or small current like 250 amps or large current like 500 amps. So when they actually do the charging, so normally the very advanced electrical vehicle, they are using 800 volts battery. So it means that the chip which control the 800 volt battery needs to be able to survive with 800 volt, meaning that you need a power semiconductor, which is more than 800 volt, maybe 1,000 volt, which can, the semiconductor chip need to be survive in that environment. So therefore, you need a special semiconductor, it's a power semiconductor, rather than silicon. And then once you have this power from the battery, you have AC, right? So DC, you need to convert to AC, and then go into the permanent magnet synchronized motor. So the whole series motion require a lot of semiconductors. At the same time, you also have some onboard accessories, like music, playing music, and playing internet. You need only 12 volt or 48 volt battery, so therefore you need to lower down the voltage. This is called DC-DC converter. You also need power chips. So overall, you have a lot of power chips, roughly 700 chips in the system. Okay, so if we talk about the power chips, typically people use silicon in the beginning because it's easy to make. So basically current actually emits, current flow from emitter, goes through this gate, underneath this gate, and then go down to the collectors. So this is a junction field effect transistor controlling by this gate here. And because of silicon, right, silicon cannot sustain at very high voltage, therefore you need to increase the thickness of silicon if you want to apply high voltage, for example, 400 volt. So therefore you need to have at least 100 micron in terms of thickness. It means that you have a lot of resistance, which is not very efficient in power consumption. You waste a lot of power because of the high resistance. So therefore, I think a better option is actually to use advanced silicon carbide. And silicon carbide, which can stand at very high voltage, more than 1,200. It means that you can reduce the thickness here to very thin thickness. Therefore, you have a better power control. Okay. And the other option is actually you can use, because silicon carbide is too expensive, very expensive, it is also not very easy to grow. So therefore, this is still challenging in terms of cost and also the manufacturability. So therefore, there's another branch. People can actually grow, epitaxially grow gallium nitride on top of the silicon, sulfide, or silicon carbide, depending on the price of the substrate. You can grow these structures. And then between aluminum gallium nitride and gallium nitride in interface here, the operation is different. So left-hand side too, basically you have a current from top to bottom. Right-hand side, we're talking about 2D electron gas flowing just between aluminum gallium nitride and gallium nitride, which is controlled by the gates. So that's a horizontal switch. So this guy basically can give you cheaper price, and potentially they can go to higher voltage. Okay. However, the growth is still very challenging if you want to get a higher quality of sample. So the other trend, basically, power devices need to consider heat dissipation, as mentioned in the morning. So basically, you have a die connecting to the heat transfer layer, and then bottom side, you need to bond it to a thermal interface materials. Then you have a heat sink to dissipate the heat, because using the power, basically, you generate a lot of heat, and which is really a detrimental effect if you don't really remove the power, remove the heat. Okay, so in summary, trend in power electronic system, battery voltage actually from 400 to 800. If you want to make a good car, that's 800. So therefore, you need to consider the power electronics. And then they were adopting 1,200 volt silicon carbide MOSFET for lower switching loss and other benefits. And also, people are thinking to use gallium nitride, high electron mobility field effect transistor for DC-DC converters to make it more efficient, frequencies higher. Okay, so last point is layout design need to be with very low parasitics, and also thermal dissipation is a critical consideration. So in overall efficiency, cost, and reliability determines whether you can build a good car. Okay, I still have 5 minutes. So the other thing is autonomous sensor computing. So the trend, basically, one simple trend is that in a conventional EV, basically you have one function controlled by one unit, electronic control units. But now up to 2025, so some of the function will be categorized into certain domain and using one computer to control, one chip to control. This will make things more efficient. And eventually to 2035, is you probably have only single supercomputer controlling all the units in the car to make it even more efficient. And the other trend is that 2020, you have a certain number of sensor, but right-hand side, by 2030, you increase a large number of sensor to perform different function. I won't really go to the detail. That's another trend. Okay, as I mentioned that if you want to do the autonomous driving, so you need to have very powerful accelerate APU. So APU is a combination between CPU and GPU, which help you to really realize a no-man car. You could just sit in and then just let it EV bring the place you want to go. Okay, so and this data basically, I would say, with the AI enhancement, so people can do a lot of things with AI. Sorry, for example, this one, sorry. So for internet user, you have your data usage is about 1.5 gigabytes per day. But for autonomous car, it's even higher, 4 terabytes. For other more advanced application, you actually increase the data usage. But anyway, 4 terabytes is already very high. So also we talk about the mainframe computing, right? This is ancient time. And then we move to personal computing. The product unit basically increased a lot. The mobile computing, and then if we go to ubiquitous computing, which include automotive and IoT, high-performance computing, mobile phone, mobile computing, you need a lot of data computation. So therefore, in semiconductor company, basically they are trying to push their technology from planar structure, which is 28 nanometer or longer, and then go to the FinFET. FinFET is between, I would say, 3 nanometer to 22 nanometers. That's a FinFET. It's still very ancient technology, but then now they're moving to nanosheet. This is probably 2 nanometer, which will be coming out next year very soon. And then, of course, semiconductor companies also pushing to look at more advanced. So 2D materials or carbon nanotube, it is anticipated probably in 10 years. That's 2035. Maybe this transistor will come out to the market. Okay, so as I mentioned in the beginning, in addition to push the Moore's law, try to make the chip smaller, more efficient, energy consumption lower, and higher speeds. The other way to do it in a simple way is to try to bind the two wafers together, top and bottom. Just bind these two wafers together. For example, APU, CPU plus GPU. You can just back to back, just do the copper bonding. Then they are connected. So this is the technology. It's called 3D fabric. And this is the commercial name for TSMC. But other companies also do the same thing. They can do the wafer bonding in order to reduce the bandwidth between these two chips. These two chips need to communicate with each other, so they as close as possible. So I think that's one very easy way to enhance the performance. Okay, in sharing, so there are many functions. I won't really go to the detail. I think I don't have enough time to finish. But anyway, there are many basic functions like occupant monitoring system and gesture recognition system, actually noise cancellation system. All these need to work in a reconciled way. So this is the sharing parts. Okay. In terms of connectivity, this is also very important. For auto driving, basically you have a V2X. V represent vehicle. To XX represent many different objects. For example, V2X represent vehicle to network or vehicle to infrastructure communication, red light and green light controller. And vehicle to vehicle, you still need to do the communication. You also need to have a vehicle to pedestrian communication. So that will help you to drive more safer. So there are sort of many benefits if we actually push the connectivity better and better. So for example, enhanced traffic safety, time saving, cost effective, environmental factors to make it more efficient in running the fuel. Okay. So this is probably the final slide. I would say V2X technology roadmap. So we are now here at 2024. I would say we start from 2022. V2X is mandatory already because you need to communicate with pedestrians, red lights, or other vehicle, right? And up to 2024 now, so it should be enabled by 5G because 5G communication is a lot more easier. So up to when we go to 2027, so we need to use advanced cellular V2X, which is 5G. It's also 5G enabled, but we need to actually use 5G cellular phone to do the communication. It becomes mandatory. Okay, so this is my final page. The message I would say, in terms of the car performance, for sensor, MCU, power chip, analog components, you don't need to use very advanced chip. 28 nanometers is sufficiently good enough, even lower technology. But for a very good car, need to have a very useful auto drive functions, you need to use APU. So in APU, probably advanced node is preferred, for example, 7 nanometer or below. So I think it's very important to control this part. Okay, and we also need to consider the cost. Lower cost in mature technology chip will be easier to build a preliminary car. But if you really want to compete with other countries, we need to think about how to make car more special, more functional. So I think the advanced chip is also unavoidable. We need to build you need to have a supply chain which can supply you an advanced chip. Okay. Okay. So that's my final page. Thank you. Thank you very much.
Ladies and gentlemen, please welcome to the stage our next speaker, Dr. Chiao Hang Lee.
So this is a flip, right? Which one is next? Oh, okay, thanks. Hi, good afternoon, everyone. And it's my great pleasure to be here to talk a little bit about the ultra-wide bandgap semiconductors for EV and also renewable energy revolution. So my name is Xiaohang Li. I'm an associate professor at KAUST. And I have been in Saudi Arabia for close to 9 years, and it's great to see how the semiconductor industry has gradually been developed in the last few years. So, yeah, so talking about EV, Professor Lansley gave a very nice introduction about what are the key chip technology in the space of EV. But in general, right, what do customers of EV want? A couple of years ago, I was lucky to sit in the Lucid car driven by the CEO of Lucid, Peter Rawlinson at KAUST. And also, if we look beyond the surface of the Earth, and certainly Saudi Arabia right now is very interested in developing the space exploration technology, right? We also have to look at the vehicle technology, EV technology for other planets as well. But overall, for customers, we want faster charging, we want longer distance, and we want less breakdown, right? And also, of course, we want cheaper price, which means better affordability. So those requirements naturally translate to 4 technical requirements. One is that if you want faster charging, you generally require higher voltage for charging, right? A lot of the EV right now are charged at around 500 volts, but some higher-end cars, such as Lucid Sapphire, charge at about 800 volts. So if you want to drive longer distance, it means that all of your electronics, especially your power electronics, has to have higher efficiency, right? So high efficiency translates to longer mileage, but also translate into the less requirement of battery capacity. And the third one is less breakdown, right? So that means that all of your electronics have to have higher reliability. And then number 4 is a cheaper price, which means you have to have lower costs in the wafer and device and IC manufacturing. So today, most of the power electronics for EV are based on silicon carbide, and some are based on gallium nitride, right? And that also includes the charging station. But in our research at KAUST, we focus on the future of semiconductor for EV. So we look at a group of semiconductors called ultra-wide bandgap semiconductors. So 2 of the examples here are gallium oxide and aluminum nitride, right? So let me talk a little bit about what does ultra-wide bandgap semiconductor mean. So semiconductor started from December of 1947 when the first transistor was invented in the Bell Lab, right? And so that was also the greatest invention of the 21st century. And if you look at the left, the silicon and germanium, which are based on the first invention of transistor, they have a very small bandgap, right? So the bandgap is probably one of the most important property of semiconductor. It represents the energy needed for an electron to be going to the conduction band in order to conduct current, right? So this is for silicon and germanium, and today silicon-based devices are probably the most important devices in the world for the semiconductor industry. There have been 3 Nobel Prizes related to silicon-based technology, and today the computing, data storage, imaging, and also a lot of the renewable energy are based on silicon technologies. And then the second wave of semiconductor technology is so-called 3-5 technology. So it is based on elements from group 3 and group 5, right? For example, like gallium arsenide and indium phosphide. So the 3-5 technology have been developed for about 70 years now, and also there have been 3 Nobel Prizes related to 3-5 technology, right? And today, the 3-5 technology are very important in high-speed applications, such as communication and so on. That includes the backbone of our internet, which is fiber optics, and also a lot of the 3D sensing technology, such as the LiDAR used in a lot of our phone to unlock the screen, is based on 3-5 technology. And the third wave of semiconductor is the so-called wide bandgap semiconductor, right? As you can see here, the bandgap, which has a unit EV, goes higher and higher as you jump to different wave of semiconductor. So the two most important materials for the wide bandgap is gallium nitride and silicon carbide. As I mentioned, they are already heavily used in new EVs and also 5G stations. And also, I suppose that most of the photons we see in this room come from gallium nitride, right? So we were honored to hear the lecture of Professor Shuji Nakamura yesterday because he was one of the inventors of blue LED, which awarded him a Nobel Prize. But going forward is the fourth wave of semiconductor, inorganic semiconductor, right? So this is the so-called ultra-wide bandgap semiconductor. So if you look at the bandgap on the left, so all of this material have a bandgap at about 4.9 to about 6.4 electron volt. And actually before, a lot of those materials were regarded as insulators, right? But as material science have progressed over the years, scientists have turned a lot of those insulators into semiconductors. So why they are important, right? Because of the very large bandgap, right? So I won't go into details here, but basically this figure right here shows that, as you go to larger and larger bandgap, right, at the same voltage, you can, exponentially reduce the own resistance or the resistance of the device. That will translate into greatly reduced, loss of the devices, right? Or it means that you can have higher efficiency. So the gallium oxide and aluminum nitride has much larger bandgap, right? And therefore, they check the box of higher voltage and higher efficiency. But how about higher reliability? And also because of the very large bandgap, they are much less susceptible to the change of environment, right? So that includes temperatures, chemical environment, radiation, and so on and so forth. So the devices and IC based on those ultra-wide bandgap semiconductor and naturally have higher reliability compared to the previous lower bandgap materials. And how about lower cost, right? So the higher bandgap does not necessarily translate to lower cost. However, at KAUST, one of our research topic is to how to reduce the manufacturing cost of those materials. So in the next few minutes, I'm going to give you a snapshot about what we are doing at KAUST. And certainly, if you have more questions, feel free to ask me later. And I look very much forward to collaborating with all the brilliant scientists here. So let's talk about cost. So as you know, the microelectronics industry, especially for logic and computing and memory, is dominated by silicon. Why is that? One of the biggest reasons is that silicon has the lowest cost, right? Think about that, like your latest phone has a processor with probably 10 billion transistors, right? So, and your phone is sold at about $500 to $1,000. So if you do the math, each transistor actually is at a cost of 10 to the minus 9 or 10 to the minus 10 US dollars, right? So that's a very low cost. So that's why silicon actually dominates most of the computing and data storage. So in order to actually make certain technologies successful, lowering the cost is actually very important. So in my group, we have used different ways to actually lower the cost of producing those ultra-wide bandgap semiconductors. A lot of the materials in the past, they are synthesized using deposition technology, right? Such as, CVD, MOCVD, MBE, sputter, and so on. But in this work, we actually use a very simple furnace, and we actually synthesize a state-of-the-art, actually aluminum gallium oxide material, which is a very wide bandgap material. So in this case, the furnace is only cost us about $10,000, right, compared to typically $1 million deposition equipment. Another work that we have carried is to synthesize this high-quality aluminum nitride on silicon substrate, right? So silicon substrate has the lowest cost, and also it is also compatible with a lot of the CMOS processes. And therefore, the ideal substrate for a lot of materials, right, whether it's gallium nitride or other compound semiconductors, is actually the ideal substrate is actually silicon. However, to grow on silicon, you have to overcome a lot of challenges, such as a so-called lattice mismatch and thermal mismatch. So in this work, we have demonstrated the quote-unquote high-quality aluminum nitride on silicon 111. And I don't know if you can see those benchmark very well. So currently, for aluminum nitride, that's less than 500 nanometer. So the aluminum nitride grown at KAUST on silicon actually has the best quality in the world compared to the other universities. So another one is high-power device research, right? So in this research, we have worked within our group. I also collaborate extensively with my colleagues. So later, Professor Hussein Al-Sharif will talk about our collaboration on the gallium nitride HAMT, right? But looking beyond gallium nitride, right? So we need to look at the aluminum nitride and on the system material like argon. They have the ultra-wide bandgap. As I said, they can withstand higher voltage and at a lower energy loss, right? So in those work, we have demonstrated aluminum nitride, Schottky barrier diode with different breakdown voltage, right? Because different application will require different breakdown voltage. For example, if you look at data center, you require a lower voltage. But if you look at electric vehicles or high-speed train, they will require much higher voltage. So in our work, we have demonstrated the aluminum nitride SPD with breakdown voltage about 200 to over 1,000 volts. And here again, in our field, it's like a competition, right? We want to compete with other universities in terms of device performance. So currently, for the aluminum nitride, we have the lowest contact resistivity compared to the other universities. So this is very important because this can reduce your energy loss during the device operation. So another work that we have done recently is the aluminum-rich argon, aluminum gallium nitride. Right? So it has also a very large bandgap. And in this work as well, we have demonstrated the state-of-the-art aluminum gallium nitride diode with very low ideality factor and very high Schottky barrier height. So those two are the so-called figure of merits for the Schottky barrier diode. So another interesting application for ultra-wide bandgap semiconductor is in extreme environments. As I said, because of the larger bandgap, they are much less susceptible to environmental changes, right? So whether we look at very cold weather or very hot weather, like the desert in Saudi Arabia, or we look beyond the Earth, right? In the future, we might become multi-planetary species, right? We need to operate our electronics at different temperatures. So in the solar system, the average temperature of planets, right, range around minus 200 degrees Celsius all the way to about 464 degrees Celsius in Venus. So how do we develop those very robust electronics for those environments? So related to the extreme environments, so there is in our area there is a magazine called Compound Semiconductor magazine, and recently we have written editorial article related to how the ultra-wide bandgap gallium oxide ICs, integrated circuits, can provide good promise for the extreme environment. So let's look a little bit about that. Right? So this is a study we have carried recently, which is we developed these ultra-robust, flexible gallium oxide transistors on a substrate that has very good mechanical robustness. So this is a bending test, as you can see here. So we have done about 20,000 bending tests for these transistors and photodetectors. And then after the bending test, the IV characteristics have just changed slightly. So it means that the devices have very good robustness. So this is very important for applications that require, that may have a lot of vibrations and other mechanical stress. Another work that we have done recently is that, hey, how can we develop, gallium oxide transistor ICs at the temperature possible in a solar system, right? So in the universe, the lowest temperature in the universe is about 2.7 Kelvin, okay? And then the highest temperature in the solar system on the planet is about 500 degrees Celsius. So how can we use this ultra-wide bandgap semiconductor to develop technology that works in those environments? Because the silicon does not work at those extremely low or extremely high temperatures. Okay, so in this work, recently we have developed the first gallium oxide cryogenic FinFET. So this is the, as you can see here, previously there are a lot of gallium oxide FinFET operating at room temperature. And our report is the first report that demonstrates this operation at 2 Kelvin. So 2 Kelvin is important for application in a space, but also important for quantum circuits, because the qubits has to communicate with external circuit for write and read operation. So you need transistors and IC that work at very low temperatures. And also this is a benchmark with the silicon FinFET technology. And in this scale, I think we are one of the few organizations and universities that have demonstrated FinFET technology that work below 5 Kelvin. Another work is our gallium oxide CMOS transistor ICs. So in this work, we target especially the high temperature applications. So the IV characteristics right here shows that the devices actually operate pretty stably up to about 300 degrees Celsius. And this is also based on our gate-all-around ambipolar transistor fabrication techniques. As you can see here, we fabricate the gallium oxide transistor on silicon substrate. And in order to achieve a very good gate control, we actually make the gate-all-around structures. Yeah, so this is a deposition of the P channel. So it looks like a sushi structure, right? It's a wrap over wrap. So yeah, so I think in this short presentation, I show you that the ultra-wide bandgap semiconductors are very important for the future of EV and renewable energy, because you want high efficiency, higher power or higher voltage, but also higher reliability and lower cost to satisfy the future demand of customers. So, and yeah, that's it. Thank you very much for your attention.
Ladies and gentlemen, please welcome to the stage our new speaker, Professor Hussam al-Sharif.
Test. Well, good afternoon, everyone. My name is Hussam al-Sharif. I also come from KAUST. And today I'm going to talk to you about a talk that is really focused more on materials, which I believe is actually a nice transition from what Lance did, talking about the big picture, and then Xiao Hang talking specifically about materials. The truth is that our group is relatively new to the area of wide bandgap semiconductors. We started a couple of years ago working with Xiao Hang. So I'm going to talk about a material that we work on in our group and see specifically how this material can do the interface engineering in some of these devices. Okay, I think something is seriously wrong with the presentation. There we go. As you know, you heard all day long about gallium nitride, how it is a material that's really up and coming and has been making a huge difference in our life. Gallium nitride-based materials in LEDs are all around us and have made a huge change. You can already see some gallium nitride in chargers and so forth. And it's new emerging applications that were touched on, from data centers to renewable energy, communications, and also EVs. And down here, I got some information about the market size for gallium nitride. You can see that it's becoming more substantial with time, and it's also covering a wide range of applications. And this requires actually engineering the devices. Sometimes not the same solution is suitable for every application, for high frequency or for high voltage. So you have to really design your device with the application in mind. So what we are trying to do here, my group is a 2D materials group. This is one area of focus for us. So our vision was in interfacing with Xiaohang is that how we can take some of the materials we are making in our lab and try to improve the performance and the quality of the devices based on wide bandgap materials, in this case, gallium nitride. So two of the materials that we are developing in our group, they are two-dimensional materials. Many of you know those, especially people in materials field, like polysulfide, like indium sulfide. So we have developed a universal process where we grow epitaxial oxides and then actually convert them by phase conversion in a process like CVD to any compound we want. We can go to molybdenite, polysulfide, 2D or non-2D materials, and then get really high crystalline quality. We also have another thrust in our group, working on a group of solution-deposited 2D materials. And a particular group of materials we have been focused on are called MXenes. The advantage of solution processing, even though it's not scalable, is that many of the devices with gallium nitride suffer from the fact that the contact material are deposited by vacuum methods that are highly energetic, damaging the interface in the process and leading to high leakage currents and very poor ion-IF ratios, which are important for a lot of the applications we are talking about. So let me just spend a few minutes telling you what these MXenes are, if you're interested in material science. Okay, so there's a group of ceramic materials called max phases. These are actually old, they're about 100 years old. These materials are known to be very tough, very strong, but they are also metallically conducting. And they usually have this general formula called MAX. M would be one of these red transition metals, and A would be one of these blue elements, and then X is either carbon or nitrogen, and more recently boron. So actually in 2011, a group of researchers so this is one thing I should say before I transition, is that there's a subscript N here. If you change the value of N, you end up with actually crystal structures, all of which are hexagonal for different types of max phases. Okay, so this material has existed for a long time. Ceramists have been working on. They are in space application. NASA uses them, blades and things of that sort. If you go back to 2011, one gentleman actually from Egypt who works at Drexel University, who was developing these materials, they were trying to say, okay, since they have electronic conductivity, good electronic conductivity, how can we make them also have good ionic conductivity? They were electrochemists, and for electrochemists, you really want a material that transports electrons very fast, but also transports ions very fast. So their vision was, if we take these aluminum atoms, the blue atoms, out, we could form structures like this one, which will transport the electrons very fast and would also transport the ions very fast. The electrons very fast because this is a metallic material, a carbide here, and the ions very fast because they have made openings for the ions to traverse and move through. And their idea was based on the fact that the bond between the metal, the black atom here, and the carbon, and the metal and the aluminum, the blue atom here, they are very different types of bonds. Their ionic character is vastly different. So if you put them in a polar solvent like HF, one bond would be attacked very fast. With silicon, it did not work. With aluminum, they were right, and they formed this group of materials called MXenes, which are actually basically as famous as what graphene was 20 years ago. So a lot of people, including our group, are trying to find applications for them. So where the name MXene comes from, this MX comes from the max phase, the parent phase I showed you on the previous slide. And this "ene" actually was added by the inventors to rhyme with graphene, because a lot of the 2D materials, people were rhyming them with graphene. So the name MXene stuck. And currently, actually, there are, I would say, dozens of these materials that have been prepared experimentally, including in our lab. And the different things about these materials and graphene is that they actually have a large compositional variation, meaning you can engineer a lot of their properties. And also during the etching process, you can functionalize the surface and basically tune their properties, like the work function, which is important for gallium nitride devices, or their plasmonic character and so forth. So the MXenes, they look like this, actually a beautiful hexagonal structure, and then each layer looks like this under the high magnification electron microscope. And if you zoom in on one layer of this, you see it's theoretically about 1.1 nanometer. This bulk section of the material here is electronically conducting. Electrons go very fast. And this section here is where the ions between the layers can go very fast. By changing these surface groups, okay, you can change their work function. You can make, for example, a better Schottky contact. You can change their plasmonic character. You can change their conductivity. So actually, I got into these materials because we had a project at KAUST working on electronics that were printed electronics, and a material like this prepared from solution with good conductivity and transparency is actually nearly ideal for this kind of application. But in our discussion with Xiaoheng and how we got to try this into gallium nitride, because we knew that if you change the work function, you could change the Schottky contact, the Schottky barrier. we could try those because the Schottky barrier is very important in gallium nitride devices. This is an example that shows you how the work function of these MXenes actually is a strong function of what you have on their surface. For example, if you have an oxygen-terminated MXene, you're going to get a high work function. But if you have an OH-terminated MXene, you can have a low work function. And we did a lot of experiments. I just show one example here by basically using organic dopants. You can actually change the surface, the work function of the MXene by nearly half a volt, which is substantial. So to make electronic devices, you really have to make thin films of these MXenes. So initially, we actually were doing bimanual spray coating here on glass, on plastic, and we were patterning this, developing photolithography techniques for patterning the MXenes. This is how they look like under the microscope, and this is kind of a single MXene flake. But recently, actually, we have developed, I don't think the movie will play here, but we have developed a process that coats these MXenes on large area. For example, this is a commercial silicon substrate that we coated with MXene. This is a quite sophisticated machine, actually. We can control the temperature, we can control the orientation, we can control the thickness, speed, and so forth. So much so, we are actually able to coat on texture substrates that are used in the solar cell. And we collaborated in the solar center at KAUST, and we actually replace the silver wires on the back of the ITO with MXene. So we have a robust and scalable process right now for MXenes. So over the year, we have a couple of years that we have made a lot of devices, but today, as I mentioned, this is my focus. So I will talk about gallium nitride devices working with Xiaoheng. So one of the first application is basically HEMT. This is basically a cross-section of a HEMT device, which works in a normally on-state depletion mode. And as you know, this thing works best when you have a Schottky contact between the gate and the top layer here. So one of the problems with these HEMTs, despite their promising properties, that when you try to put a contact material on top of the stack by techniques like sputtering, by techniques like evaporation, it turns out that you do some damage to the interface. You can create defects. And more importantly, these defects, if you do subsequent thermal annealing, are going to diffuse in the structure. And when they diffuse, they introduce states in the gap, defects in the gap, which can actually degrade your gate current, and they can degrade your ion-off ratio. So the concept was, what if we actually use MXene to replace, let me go back here. What if we use MXene to replace that gate material? Because MXene is done by soft deposition method. There is no energy, there's no sputtering, there's no evaporation. What would it do to the interface? What would it do to the properties of the HEMT? So basically, this is the schematic of the experiment we carried out. Okay, we did the conventional HEMT structure using gold nickel contact, and then we use MXene. So I'll show you the data in a minute, but our characterization essentially reveals this picture. In the case of MXene, you do not actually react to form a chemical bond with the interface, and there's a gap there because this is like between the layers of MXene, there's this Van der Waals type of gap. So essentially, you don't really introduce defect states in the gap like you do in the case of nickel. And if you do depth profiling, you will see in a gallium nitride structure with the nickel gold, there is diffusion of the nickel into the algan layer. But in the case of Maxine, we don't have this diffusion. So there's a lot more characterization, but in a nutshell, the result of this study showed that, that you can actually, with Maxine, contacts produce the same output curves, actually with a little bit better saturation here than you have with nickel gold. And if you do additional characterization on this, you find that actually the ion-IF ratio, because of this improved lower I-off here, the ion-off ratio is actually increased by 3 orders of magnitude. And this is for the nominal, excuse me, for the nominal Maxine. On the other hand, if you use oxygen-terminated Maxine, which has a higher work function, we can reach 10 to the 13. This also comes with a very sharp swing, subthreshold swing, nearly ideal actually, and a voltage of about 1085 volt with a significantly higher mobility for Maxine. And I think Xiaohang showed this picture. This really beats a lot of the other. Thank you very much. I'm actually recovering from a severe cold anyway. Thank you very much, Nazik. So that was one area where we showed that the Maxine interface can actually improve the quality, reducing the defects and reducing the diffusion, resulting in substantial improvement in actually the performance of the device. Similarly, along the same lines, we actually thought about looking at Schottky photodetectors. You can make photodetectors from gallium nitride in different ways, okay? But one of the ways you can make that is simple and easy to fabricate is actually using the Schottky type of contact. So we use the same reasoning. If Maxines have a friendly or let's say a high quality interface with gallium nitride, why not use it to try to make photodetector? So we made this and we characterized the Maxine by itself and different substrate, compared how it goes on gallium nitride, and we found out there's really the growth of Maxine on gallium nitride doesn't really fundamentally change its structure. And you can characterize these diodes basically. They are in fact self-powered because of the large Schottky barrier at the interface between the Maxine and the gallium nitride. You can get a driving force for the carriers to collect the carriers, and therefore these are self-powered. You don't really have to bias it. So you can see the curves here, and if you focus, for example, at 360 nanometer, we plotted nearly 20 sites across the wafer here, showing reasonably good uniformity and a large ion-IF ratio. These actually, for a 2D materials, they perform very well, in fact. So the responsivity is about 682 milliamp per watt, and the detectivity is up to 7.6 times 10 to the 13 with a fairly fast rise and volt time. You can also compare this to some of the literature, and you see that these Maxines, despite being a solution deposited contact, is actually producing a fairly robust photodetector. I would not say it's perfect, but it certainly looks that this concept of using soft deposition of a contact material with a tunable work function on top of wide bandgap semiconductor is something that is definitely worth pursuing. And these are some publications on this, okay? And you can see that our Maxine, because there's a lot of know-how about Maxine, how you functionalize it, what work function you get actually can produce much better results. Finally, this is not about Maxine, but this is about our process where we start with a universal growth of oxides, epitaxial oxides, and converting them to different layers. You can make molybdenite, and then if you transfer that, we have shown that you can put this on an amorphous substrate, and because of the molybdenite lattice constant, you can actually glow gallium nitride directly on an amorphous substrate. We're trying to scale this up because this will allow you then to actually have a much cheaper substrate. And finally, this field of Maxine electronics, we believe there's a lot of stuff to do there. Okay, there's many devices you can use Maxine. Of course, there are challenges. We are working on them. We have a fairly robust program on this in our group. And I'll give you just one example in one of the other areas. There was a talk earlier about the Josephson junction for qubits and things like that. We actually have induced superconductivity in Maxine by changing the functional group on the surface. If you go to nitrogen, this is niobium-based Maxine. Niobium nitride is a semiconductor material. Creating these bonds on the surface of Maxine actually induces superconductivity with this material. And with that, I would like to thank you for your attention.
Ladies and gentlemen, please welcome to the stage our next speaker, Professor Edward Yi Chang.
Hello, my name is Edward Yi Cheng. I'm from NYCU, Taiwan. Maybe you wonder why I'm here. My student, former student, PhD, Dr. Deepak, works here, and he told me that there's a huge semiconductor forum that will be held here. And I was wondering why there's no speaker from Taiwan, because Taiwan is a very important manufacturing research country for semiconductors, so that's why I'm here. Okay, and as for future semiconductor, I think gallium nitride is definitely the number one, which will come into reality in very short period of time. And during the last few weeks, people are talking a lot of applications. For example, the PV, EV, the data center, and for example, the charger, or different type of chargers. They all need gallium nitride devices to save the energy, and that will be realized in a very short period of time. And then to use these kind of different applications, actually what we're talking about is just a basic gallium nitride hemmed structures with the basic functionality. But for so many different kind of applications, there need a lot of innovation in tuning the device structures and in the process and new materials. So here, I'm just focused on two applications, the EV and PV application, how we can further design the device structures and material to make the gallium nitride suitable for EV and PV applications. So my topic is gallium nitride power HEMS with a ferroelectric gate stack for EV and PV application. That means it's a gallium HEMS, but for real application, EV and PV, you cannot just use it. The best way is to add some ingredient to process all the materials. And here, the ingredient is a ferroelectric gate stack that will make them maximize their functionality. So my talk will be introduction and our innovation pattern for gallium nitride power devices, and then why we need a novelty of technology, and then demonstration of the devices, and finally go to conclusion. Gallium nitride properties, I think we know a lot. But here, we know that for power device and high-frequency device is basically the most important application for gallium nitride right now. And that's because gallium nitride very high electromobility that make them to have a very low on resistance and channel resistance, and also make them to be used for high frequency. And the other important aspect is the breakdown voltage, breakdown field of gallium nitride, which make them to be used for high breakdown voltage. And especially right now, we need not only low breakdown applications with high current, but we also need a high breakdown above like 1,000 for high power applications. So these are the different applications for gallium nitride, from low voltage to high voltage. And based on that, we need to tune the device structures and the device materials so that they can apply to different category with very high performance. So right now, I think there's already we have shown that there's a charger, USB-C chargers, and we have a lot of people working on the wireless charger, okay, which we also work on. And then we know that they were used in many power supplies, power source for laptop, okay, and also up that there's applications for EV applications. Okay, and for EV application, PV application, there's special need because this application we need to be normally of technology. And here we use ferroelectric engineered charge trapping layer as a gate layer to provide E-mode gallium nitride mixed HEM device for these kind of special applications. So usually for this kind of power device, for this EV PV application, we need a very high threshold voltage. That's because we need to avoid 40 turn on. Because if it's 40 turn on, the car will keep on going, and then you cannot stop them. Okay, then there could be quite a big damage it could cause. And then we need a high drain current because we need for power device we need a high power, so we need a high current. And then we want to save energy, so we need low on resistance. That means your channel resistance must be low. Your mobility must be high. Your carry concentration must be high. And then we need high breakdown voltage because that's nature of high power devices. We need a very high breakdown voltage, operation voltage. And then we need to reduce the gate leakage. Of course, for this kind of important application, especially for high power, we need to have reliability. And that means we have to solve the current collapse and threshold instability type of material device characteristics for this kind of gallium nitride device. So this is just show you the signal why we need a normally of devices. Okay, because basically we need normally of device. But if we turn it on, and if it turn on and voltage is too high, okay, and the threshold voltage is too high, then you would cause accident turn on, and you cannot stop them, okay? So you can see that if there's a surge in signal, then it will be 40 signal, okay, what I mean 40 signal, above the threshold voltage, then the car will turn on, and then you may have accident that you cannot stop the car, okay? That's why we need a normally off device with high threshold voltage, okay? That's one of the key issues, okay? And how can we get high threshold voltage, okay? Usually the device is we apply voltage, we can turn it off, okay? And then if we want to turn it on, then we have to turn the voltage on. For E-mode device, so we have to turn it on. And the turn on about certain voltage, they will start work. And we need to have a VTH high, just like we say that if the VTH is low, then if there's a surge due to the faulty signal, then the car will turn on. So we need a very high VTH, so this will not happen. So how can we make a device with high VTH? The VTH by nature, the device nature, but we can design the devices, okay, with the ferroelectric layers. And the ferroelectric layer, when you apply a voltage to it, it will create an electric field, okay? Because of polarization, okay, it will create an electric field against the voltage you apply it. So you need to apply an even higher voltage to turn it on. So that's why this device works, okay, at a very high threshold voltage, and that provide the safety operation of this kind of device in EV or PV applications. So these are the actually this ferroelectric layer needs special design, and we are using hafnium nickel oxide with a superlattice and sandwich between aluminum oxide. And aluminum oxide is just to reduce the leakage current, okay? And hafnium nickel oxide, we used to create the ferroelectric material. So the polarization will be high. We put in a huge layer, so the polarization electric field will be high. So you will have high electric field, okay, to achieve high threshold voltage. And of course, it's not so simple. We have on the bottom a hafnium oxide nitride and aluminum oxide. Last hafnium oxide nitride is a charge storage layer, which gives you a lot of charges, negative charge. Aluminum oxide is to prevent the electrons leak through the whole stack of the ferroelectric material. Okay, but overall, you need a special design, so you have an electric field. Okay, you have first the ferroelectric material with the electric field opposed to the electric field you applied, and then this must be high enough to create high enough electric field, so your VTH will be high enough so that you can when you have a 40 turn on, it will not turn the device on. Usually the voltage required is above like 2.5 volt, okay? And by regular device technology, usually several technologies being used to make this normally on device, but usually the VTH is too low to have this kind of safety margin. Okay, so this kind of a ferroelectric material is hafnium oxide and hafnium nickel oxide. And this is not a new material system. It's this system has been used in memory, okay, for quite a long time. So and also it is scalable, okay, because it's a semiconductor technology, okay. So based on this kind of past history, so we are quite sure they can be used for this kind of semiconductor device application. And we show you the evidence that this can actually operate at a very high operation voltage. So these are the key layers that I mentioned with aluminum oxide, hafnium nickel oxide, and we sandwich them, and then we have charge trapping layer and aluminum oxide. So these layers will reduce leakage current, and it will create very high polarization and create a lot of electric field that will oppose the electric field you apply to it. That's why you get a very high VTH, very high threshold voltage. So this again show you the layers. Okay, hafnium nickel oxide, and then and this layer is laminated, and then to reduce the leakage current. So so this is the Venn diagram during the operation. Okay. Okay, and this of course is not straightforward. Okay, and we need to do some treatment on the layers, so to make sure there is no defects, no defects, and no instability for the VTH. And also we use fluorine treatment to increase the polarization, okay, so that the VTH can be further improved. Okay, so this is after all these efforts have been done, we can reach threshold voltage around 5.4 volt. And I was just mentioned that 2.5 volt is far more than enough for this kind of application. And most of the technology that proposed cannot reach such a high threshold voltage. And the current, of course, you are using this for high power device. So when you reach very high threshold voltage, the other characteristics cannot be sacrificed. For example, the current and the R-on, which determine your energy consumption, and your breakdown voltage must be remain high. And then your own resistance, that means at a high voltage, your resistance cannot be changed. Okay, they can remain very low. Okay, because there are many the charging defect state within the structures. that is under control. Okay, and that's how we achieve this kind of emo devices. Okay, and that kind of device we have tried a few ways to further improve it, and one of the way is to have Okay. Wait a minute. Okay, one of the how we turn it back? Okay. Okay, so we use Tri-Gate, okay, just like a silicon FinFET. So we make a fin, and then we use the same Tri-Gate technology, and we put them together. So for this kind of device, you have 2 DEG channel electrons and also the inversion layers. So you have more electrons, and then you in the channel, so you have a higher current and low on resistance. And in that way, the performance is better than the planar, okay, devices. Okay, so this is the characteristics. Okay, you can see that it's a E mode with a high current, okay, and also the on resistance is very low because the current is very high. And other characteristics are all improved. So these are the key factors, okay, that is improved by using these Tri-Gate structures. So we can see that the ID maxima, the current improved, and your on resistance improved, okay, and also your breakdown voltage improved. Okay, and this kind of device, of course, the most important thing is for the reliability. Okay, so for this kind of new structures, we have tested, and it's proven that if your gate is around operate at 13.38 volt, they can last for 10 years with only very small failure. Okay, so this is totally meet the industry requirement. And also there's a lifetime, okay, is also being tested. And also we have tried new semiconductor materials. Okay, we use aluminum gallium nitride, and we use Indian aluminum gallium nitride hemp, and which had even higher polarization. So we can use very thin layer to increase the current. And meanwhile, the breakdown remain the same. Okay, so we can see that with this kind of new materials, we can improve the current more than 15%, okay, or 40%. And that's also good for the power devices. And then we put a feed plate, okay, to increase the breakdown voltage, to reduce the peak electric field and improve the breakdown voltage. Okay, and then by that we also design the field plate morphology so that the capacitance can also be reduced, so they can operate at a very high frequency. So these are the comparison, okay, for different type of field plate. Okay, so this kind of a power device, gallium nitride power device, can be used for quite a huge application in car. For example, wireless charging, which we already do many work on that, and also wireless charger, and also the electric vehicle charger, and also LiDAR application, and solar cell panel. Okay, those are quite a few applications that I address here. And this is the LiDAR application. Okay, we use gallium nitride as a source to drive the radar. Okay, and in that way you have a higher, because gallium nitride operation frequency is higher. Okay, so in that way you can have higher resolution, higher and higher precision, and because this is high power, so you can have a long distance. So compared to the commercial LiDAR, which is not using this kind of gallium nitride technology, we have a higher frequency. That means your response time is quicker. When you use as a LiDAR, they can respond very quick, so can avoid car collisions, okay, more easily. And the breakdown is high, and on reason is low. So we did this kind of gallium nitride applied to the LiDAR, then you can actually improve LiDAR accuracy and the safety. And in the beginning, we talk about that for this kind of gallium nitride device, important thing is to improve the device itself and also to combine with the system itself. So the focus we put on is to improve the device itself. So because this kind of high voltage inverters, okay, you can see that they can have glitches on the capacitor that will exceed the VTH that can cause the force trigger and result in shoot-through fault. Okay, so for this kind of application, the threshold voltage must be high. So in other way, you need to use this kind of E-mode, okay, ferroelectric E-mode to prevent this kind of faulty operation of this kind of system. And also, is the same for the inverter, for the PV micro inverters, okay. And parasitic inductance could occur during these kind of phase lags that will also create voltage glitch and cause force trigger and make the whole system fail. Okay, so again, high VTH system can be applied for these inverter applications. So overall, we have proposed a new concept to overturn both high threshold voltage, high current, and with the so-called with the designed ferroelectric charge gate stack, and which have a very high VTH and high current. And this is due to the very strong ferroelectric correlation, and that is the result of our design of the ferroelectric gate stack. Okay, and the reliability of this kind of structure has been tried, okay, and tested, and they show very good results. And we have also shown that we can use the tri-gate structures, new tri-gate structures with this ferroelectric gate stack, and new material, Indian aluminum gallium nitride, new material used to make this kind of E-mode device with higher current and even lower dynamic RO. So that's a further improved, okay. And then overall, we have shown that E-mode gallium nitride power device are prevented for various power switching applications. So include EV and PV applications. And of course, gallium nitride application is much more than this. So for different kind of application with higher power, there could be some small modification in the device, and the circuit is necessary to not the things that we already developed can meet all the system requirements. So I think each one had to be carefully designed, okay? And I think the four previous speakers, like Li Lianzong, were talking about how we can work with KSA to cooperate. Oh, KSA was the roadmap for the KSA for this kind of new technology. I think working with us on the power device is one way for this kind with KSA is one way we can work together to make a new device for future power applications. Okay, thank you very much.
Ladies and gentlemen, please welcome to the stage our next speaker, Mr. Ian Wright.
Good afternoon, everybody, and thank you for your perseverance. I think I'm the last speaker today, so hopefully I don't disappoint. A little bit different. I'm not a device guy, so those of you that don't need to worry about that. What I'm going to be talking about today is silicon carbide. We've been speaking today about power devices for EVs. Silicon is there, gallium nitride is there, silicon carbide is the other player. And in some modules, all three are used, so nothing is going to be taking over from anything else. And what we're looking at today, one of the comments before was silicon carbide is very expensive. It is very expensive. It's expensive because yields are very low, also the different process flows and different steps at the moment, still in fairly early stages, even though the material has been around for many years. And we have developed a quite disruptive technology to provide a very, very good surface on which to grow the epi with better performance, but also at a much lower cost and also much better for the environment. So very quickly today, I'll just one slide on who we are. We'll go through the technology. We'll look at some of the characterization that we're doing on that on the material as well. Oxford Instruments has been around for 65 years. It was a spin out from the university. We're well over 2,000 people now around the globe. I'm based personally in Singapore and travel everywhere between Turkey and Japan in my job. And for the semiconductor industry, we have 4 divisions out of the 8. I work for the etch and deposition, the fabrication division, but we also have characterization tools. And I'll speak a little bit about the Raman microscopy that we're using on the characterization of our process this afternoon. So plasma polishing, there are 3 basic channels to this, or pillars. And I'll go, let me go back one. One, firstly, it's a selective etch, it's contactless, and it removes the subsurface damage in the silicon carbide, which is really inputted through the grinding and CMP steps. And we try and remove this before the silicon carbide epi is deposited. It's much, much lower cost than CMP from an operating point perspective, and it's also a much cleaner process from an environmental perspective as well. So the whole process flow, if you take your silicon carbide boule, you have to make the wafers, as you saw earlier on. The boules are very small. You only get maybe 10, 14, 15 wafers from each boule, typically either laser separated or with a diamond-coated wire. You then go through various grinding and CMP steps, and you're left with a very, very smooth, very, very flat, but really often damaged layer. So this is what we're trying to do. After the grinding step, we're looking to offer a different way to polish the surface prior to the epi. So typically, after grinding, it goes through a CMP step, very, very flat, maybe 0.1 nanometer, very, very flat. But in the surface, there is damage, there is impregnations within the surface. And I say we have a pretty poor surface on which to grow your epi. We use a relatively standard plasma etch tool with a few modifications, both hardware and process-wise. And although we do not planarize, we cannot get it as flat as CMP, it's already quite smooth. I mean, we actually do smooth it, and typically we get this wavy surface. But this wavy surface might only be 0.5 nanometer, but obviously it's a little bit higher than a CMP surface at 0.1 nanometer. But the big thing here is it is damage-free. So on the left here is an image of after plasma polishing. The dark lines, many people say, well, these are scratches. No, they're not scratches. This is just the undulations in the surface. But you'll see the two examples here. Once we've grown the epi on our wafer on the left, and once we've grown epi on a CMP'd wafer on the right, they look identical. They are now as flat as each other, around about 0.12 nanometer. So visually, they are now the same. So what are we trying to do here? We're trying to obviously at least supply as good, if not better, performance than a typically CMP'd wafer. We're looking to provide at least as good, if not device yield, because obviously there's no damage in there. We should get higher yield. Same with performance. Our systems can, if people want, be obviously put in a clean room. That's their normal environment. Although we can sit next to a CMP system as well. We don't mind. But it's no contact. So again, less chance of any breakage, the ability to go to thinner wafers as well. Cost of ownership, we see up to an 85% reduction in the operating cost. Capital cost a little bit higher, but it's really, really totally outweighed by the operating costs. If we get increased yield as a further cost reduction, the ability, because there's no contact, to go to thinner wafers. It's a much more stable process. Plasma processing, cross-wafer, wafer-to-wafer, run-to-run, very, very stable. Less downtime. There's not a lot of cleaning with these systems. We open the chamber once a month. And we can scale from 6-inch or 4 to 6 to 8 with no issue at all. We're using very, very similar process. And thirdly, and very, very important, obviously for a country like Saudi Arabia and other Middle Eastern countries, it's very, very environmentally friendly. We use no water. We're using no slurries. There's no problem with treatment of those gases, those materials. Some of the proof, obviously we have to prove the device works. So a small system here where we've done plasma polishing. It's a dry etch, and we've compared with the CMP reference. Very, very stable on the yields for the plasma polishing. But on the right, you'll see the wafer on the right. After epi growth, there was a drop in yield. Now, prior to the epi growth, that wafer looked perfect. And the problem only came after the epi was grown. So that wafer now is either scrapped or it's going to have to be reclaimed. If we'd done the plasma polish, we could have removed the damage that is evident there. So I say we're using a fairly common industry standard plasma tool. Cost reductions, we're looking at almost $30 a wafer for 6-inch, close to $50 a wafer for 8-inch. Our tool pays for itself in 6 months. Much more stable process and results. I say we talked about thinner wafers as well. And there are 3 ways. We can either totally replace the CMP. We can do a hybrid method. The issue in silicon carbide is nobody does the same thing. There are no standards at the moment. So we're having to cater for different people's process flows. And sometimes we even do a small plasma polish after the CMP as well, depending on their requirements. Obviously on CMP has been around for many years. It's not going away. It's standard in silicon, but it's the biggest user of water in the whole semiconductor industry. Slurries people now, even in silicon carbide fabs, are delivering by the tanker load using an awful lot of slurry each year in addition to the water. But with plasma polishing, there is no water. We do not need it. It's a dry process totally. We're using very standard gases which are abated as soon as they come out the back of the system. So from a point of view of environmental issues, that's minimized to a very, very high degree. I think this is all, some of my animation might have gone here, but okay. Now, we spoke a little bit, actually, I can't remember the focus here. Is that the one? I'll come in. So in the middle is where we were talking about doing the pre-epi, but this process can be used in many stages of the silicon carbide wafer formation, whether it be at the start, whether it be at cutting the thinner wafers, whether we do stress relief on the front and the back of the wafers. We were talking about the polished pre-epi. We're also doing post-epi work as well, so we're smoothing the epi, we're reclaiming, we're thinning the epi. And even now we're talking people even with the device stage. Interfaces within the device are very, very important. There are lots of process integration issues, and we're talking to many people on this area as well. One slide I want to show today is that other parts of our business are into characterization, and we're utilizing both EBSD, Raman microscopy, and contact resonance AFM for the characterization. I just want to show you this is Raman microscopy. Depending on the modes that we look at, we scan the whole wafer. It does take quite a long time, but it's still very fast for what it does. And just examples here of what can be done. We can look at the doping density and the doping uniformity across a wafer. We can look at the stress and we can quantify it. We can tell whether it's compressive or whether it's tensile. And from the same data that we've collected from the one scan, we can even look at warpage as well. And we can do this on the surface. We can do this at any depth within the wafer. So, real brief introduction to one of the things that we're doing. We also do work on gallium nitride. We do a little bit of work on gallium oxide and diamond and these other materials as well. But one of the big messages we say is that low roughness, which CMP will give you, is not a good idea of giving good surface quality. It's one of the main quality inspection units for an epi house or a wafer provider, but it does not guarantee you a good quality wafer to work with. So the traditional polishing processes do leave behind, not always, but quite often, surface and near surface defects. Plasma etching removes them. We've now released plasma polishing for 6-inch. We're getting the 8-inch qualified now. The process is the same, which is why our cost of ownership gap is that much better for 8-inch. Lower cost of ownership, very, 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 very environmentally friendly. And I say a very, very brief introduction of just one of the technologies we're using for characterization, but the other ones we also use for crystal quality, obviously AFM for the topography of the system. So thank you for your attendance. Quick one, an easy one to finish with. I think maybe a little bit easier than some of the device work. So thank you for your time. Thank you.
Ladies and gentlemen, please welcome to the stage Dr. Thamer Tabbakh for the closing remarks.
Ladies and gentlemen, esteemed speakers, valued sponsors, and the dedicated volunteers and organizers. As we wrap up the third Future of Semiconductor Forum, a joint effort by CAX and KAUST, I want to express my deep gratitude. Over the past 2 days, we have enjoyed insightful discussion, innovations, idea, and a strong collaboration, which truly reflect the future of semiconductors. Our speakers have shared the latest industry opportunities and the challenge inspiring us all. In this forum, His Excellency
has made several impactful launches that will shape the future of semiconductor, such as the joint master program between University of California, Los Angeles, Prince Nora University, and CACS. Also, the Semiconductor Ignition. Lastly, but not least, the National Capability Center between CACS and KAUST. I also would like to thank our sponsor for the generous support, which has been crucial to the success of this forum. Your dedication and advising the semiconductor industry is greatly appreciated. I also extend my sincere thanks to the organization team, CACST and KAUST, who worked tirelessly behind the scene. Your hard work ensure everything runs smoothly. The future of semiconductors look bright. The energy and innovation we have seen assure me of that. Let us use this momentum from this forum to explore a new opportunity, push limits, and build the future of semiconductor together. Thank you once again for being part of this remarkable forum. Let's continue this important conversation and keep the spirit of collaboration alive. Thank you.